at 3:47 in the afternoon Central Daylight Time, a weather station in Death Valley, California, just recorded a surface reading of 129 degrees Fahrenheit, and a separate station in Needles, California, crossed 122 degrees before the sun had even reached its peak angle for the day. Those are not projections, those are observations. Those are numbers that already happened. And they are happening during what the National Weather Service is now calling, in its own operational language, a heat event of historic magnitude across the continental United States. If you are watching this from anywhere between the Sierra Nevada and the Mississippi River right now, the air outside your door is not the air you grew up with. It is not the air your infrastructure was designed for. And it is not the air the forecast models predicted you would be breathing this week. Welcome to the Cosmic Forecast. I am glad you found this channel tonight, because what we are walking through in the next 2 hours is the raw data from federal agencies, peer-reviewed atmospheric research, and operational forecast products that most people will never see in a headline. The picture that assembles when you put all of it together is not just a heat wave. It is a diagnostic reading of a planetary system that is behaving beyond the boundaries of the historical envelope that every one of our prediction tools was calibrated against. Stay with me until the end. If this has you hooked, subscribe to the Cosmic Forecast so you do not miss what comes next, because this story is just getting started. The heat dome has not moved. The overnight lows are not recovering. The grid load records are still being broken in real time. And we will be right here when the next piece of data lands. Drop a comment below. I want to know where in the world you are watching from, what time it is where you are, and your honest take on this question. If the atmosphere is operating in the tail of the statistical distribution 3 months out of every 12 now, when does the tail stop being the tail and start becoming the middle? We genuinely want to know what you think. Now let us get into it. Something has broken in the way we talk about heat, not the way a broken thermometer breaks where the number is wrong. Something has broken in the way a category breaks, where the number is right but the category no longer contains it. Let me show you what I mean. On July 7th, 2026, the Salt Lake City International Airport recorded a temperature of 108 degrees Fahrenheit. That reading in isolation is a hot day for Salt Lake City. Uncomfortable, dangerous for the elderly and outdoor workers, sufficient to trigger a heat advisory, but not by itself historic. The historic part is what was happening around it. That 108-degree reading came at the end of a 14-day stretch in which the daily maximum temperature at that same station never dropped below 100 degrees Fahrenheit, 14 consecutive days above the century mark. The previous record for that station, set during the summer of 2007, was 9 consecutive days. This new streak did not break the old record, it nearly doubled it, and it is not over. The forecast, as of the model runs from this morning, shows the pattern extending at least another 6 days. Let me put that in a framework that actually means something. If you took every summer between 1874, when the National Weather Service began keeping continuous records for Salt Lake City, and 2025, and asked how many of those 152 summers contained a 14-day plus stretch of triple-digit temperatures, the answer is 0. Not 1, not 2, 0. The current stretch is the first of its kind in the modern instrumental record. And it is happening in a summer that meteorologists have already flagged as the driest, hottest opening to July on record for a swath of the interior West that extends from the Great Basin across the Colorado Plateau and into the southern Rockies. Now, the temperature itself is only one layer of the story. Here is the part that should stop you cold. The forecast issued by the National Weather Service office in Salt Lake City on the morning of July onest called for a peak temperature of 104 degrees on July 7th. The actual observed reading was 108. 4 degrees over forecast might sound trivial. It is not. It is part of a documented pattern that has been repeating across dozens of stations from Boise, Idaho to Amarillo, Texas for the past 2 weeks. The models say 101. The sky delivers 104. The models say 106. GATSCA delivers 110. Day after day, station after station, the observed temperatures are running 2 to 4 degrees above the model output. That gap has a name in operational meteorology. It is called a systematic warm bias in the observation minus forecast residual, and when it appears across a continental scale event, it is not noise. It is a signal that the atmosphere is doing something the models were not trained to represent. Weather models are not toys. They are the most sophisticated fluid dynamics simulations ever built by any species on this planet. The global forecast system operated by the National Centers for Environmental Prediction runs on supercomputers capable of quadrillions of calculations per second. The European Centre for Medium-Range Weather Forecasts model, widely considered the most accurate operational model in the world, ingests over 40 million observations every 12 hours from satellites, radiosondes, aircraft, ocean buoys, and surface stations to initialize each forecast cycle. Within a 1 to 3 day window, the models are accurate to a degree that would have seemed like sorcery to a meteorologist in the 1970s. They resolve pressure systems down to grid spacings of 9 kilometers. They account for terrain effects, radiative transfer through the atmosphere, phase changes of water in cloud microphysics, and dozens of other variables interacting in non-linear ways. So, when these models, these precision instruments, systematically underpredict temperatures by 3 degrees for 2 consecutive weeks across a region the size of Western Europe, that is not a routine forecast miss. That is the models telling us something structural. Let me say that again, so it registers. The best atmospheric prediction systems humanity has ever built are running behind the atmosphere, consistently, measurably, across a geographic area larger than most nation-states. And the direction of the miss is always the same. The atmosphere is hotter than the model expected. Never cooler, never symmetric around the forecast value, always hotter. When a bias runs in one direction only, statisticians and meteorologists both know what that means. It means the model's underlying assumptions about the state of the system are anchored to a version of the atmosphere that no longer quite exists. And this is where the story gets deeper than a headline about heat. Because if the models are systematically underestimating an event that is already historic, the operational implication is that every heat warning currently being issued across the United States may be describing a floor rather than a ceiling. The stated high of 112 might be the safe assumption. The actual peak might be 115. And the emergency planning frameworks that determine when to open cooling centers, when to dispatch mutual aid resources, when to trigger utility load shedding protocols, are all calibrated to model output. If the model is behind reality, the response is behind reality. And in a heat event, being behind reality is measured in bodies. Now, hold that thought, because it connects directly to the next layer. The atmospheric configuration that is producing this event is not just intense. It is structurally unusual in ways that the upper-level data reveals only when you look at the right variables. Picture a standardized exam taken by 1,000 students in a single classroom. Most cluster in the middle around the average. A few dozen score well above that. A handful reach the upper decile. 1 or 2, at most, score in the 99th percentile, meaning they performed better than 990 out of 1,000 peers. That is what statistical rarity looks like when you can visualize it. Now, apply that same framework to the atmosphere itself. The National Weather Service Weather Prediction Center in College Park, Maryland, issued an operational discussion on July 5th, 2026, in which the forecasters described the upper-level pattern over the central and western United States as, and I am quoting verbatim, at or exceeding the 99th percentile of the climatological record for early July, with mid-level heights over the Four Corners region approaching values that have no direct analog in the historical database. That last phrase deserves a moment of attention: no direct analog. In the language of operational meteorology, that means when the forecasters searched their reference database of past atmospheric patterns to find a comparable event to use as an analog for the current situation, they could not find one. The pattern is outside the file of historical patterns. Let me translate what mid-level heights actually means, because it is one of those phrases that sounds abstract until you understand the physics. The atmosphere has layers of pressure. At roughly 18,000 feet above sea level, there is a pressure surface that meteorologists call the 500 millibar level. The physical height above the ground at which the air pressure drops to 500 millibars fluctuates depending on the temperature and density of the air column below that surface. When the atmosphere is warm and expanded, that height rises. When the atmosphere is cold and compressed, that height falls. The 500 millibar height, in other words, is a direct measurement of the total heat content of the lower atmosphere over any given point on Earth. During a normal early July, the 500 millibar height over the Four Corners region averages around 594 decameters, which is 5,940 meters above sea level. During a strong heat wave, that height might climb to 597 or 598 decameters. During a genuinely extreme event, it might reach 599 or 600. On July 6, 2026, the observed 500 millibar height over the Four Corners was 604 decameters. Let that number breathe for a second. That is 6,040 meters. That is roughly 40 meters above the highest 500 millibar height ever previously observed over that region in the entire modern radiosonde record, which extends back to the 1940s. It is not just a record. It is a record that clears the previous record by a margin approximately equal to the standard deviation of the entire historical distribution. That is what an unprecedented outlier looks like in the upper atmosphere. Now, the 500 millibar height is only one variable. Meteorologists also look at something called the thickness, which is the vertical distance between two pressure surfaces, typically 1,500 millibars. Thickness is even more directly a measurement of the average temperature of the lower half of the atmosphere. The thickness values being observed across the interior West this week are running 2 to 3 standard deviations above the July climatological mean. That is the language of extreme events. 2 standard deviations is the boundary of what meteorologists consider a truly rare occurrence. 3 standard deviations is the domain of once in a generation. The European Centre for Medium-Range Weather Forecasts operates a diagnostic product called the Extreme Forecast Index, or EFI. It is specifically designed to quantify how anomalous a forecast event is relative to the model's climatological baseline. An EFI value between 0.5 and 0.8 is classified as unusual. Values between 0.8 and 0.95 are described as extreme. Values above 0.95 are exceptional. The EFI values being generated by the ECMWF model for maximum daily temperatures across the American Southwest this week are consistently in the 0.9 to 0.98 range across a geographic area covering multiple states simultaneously. A companion diagnostic called the Shift of Tails measures how far the extreme values of the forecast distribution have shifted relative to the climatological extremes. Shift of Tails values approaching 2 indicate that the current forecast extremes are not just at the edge of the historical distribution, they are pushing beyond that edge. The models are saying, in their own mathematical language, that the atmosphere is generating conditions that exceed the outer boundary of what the models have been calibrated to represent. Think of it like a ruler built to measure every heat wave humanity has ever observed. Every European heat wave of the 20th century. The Chicago heat wave of 1995. The Pacific Northwest heat dome of June 2021 that pushed Portland, Oregon to 116 degrees Fahrenheit. That ruler was built with those events at the extreme tick marks. What is happening across the American Southwest right now is bending the ruler at its extreme end, not breaking it, not shattering it, bending it consistently in the direction of higher heat content. And here is the historical context that separates this event from those earlier benchmarks. The 2003 European heat wave that killed an estimated 70,000 people occurred in August, at the climatological peak of Northern Hemisphere summer, over a continent whose oceanic surroundings deliver moderate rather than extreme summer temperatures under normal conditions. The Chicago heat wave of 1995 that killed over 700 people occurred in mid-July, again at climatological peak. The Pacific Northwest heat dome of 2021 occurred in the final week of June, immediately following the summer solstice. All of those events happened when the seasonal machinery was at or near maximum. What is happening right now is happening in the first 10 days of July, which is climatologically warm, yes, but not the peak. The peak for most of the affected region is not until mid to late July. We are 2 to 3 weeks ahead of the annual heat maximum, and we are already at or above the 99th percentile of the historical distribution. The next question that should be forming in your mind, the one that atmospheric scientists are quietly asking each other in email chains and Slack channels this week, is not what the peak of this event looks like. The question is what happens when the peak of this event lands on top of the climatological peak of the season. Because those two peaks are still to come, and they are going to arrive layered on top of each other in a way that the historical record does not describe. And when you look at the geography of where this pattern is affecting the country, the answer starts to take on dimensions that no single station reading can capture. Part 3. The scale that is the anomaly. Take a map of the continental United States and lay it flat in your mind. Not a political map with state lines and highways, a weather map. A single frame frozen from the atmospheric movie playing across the country right now. In the Southwest, temperatures are running 15 to 20 degrees above the July climatological average. Not 5, not 10, 15 to 20. Across the southern plains, dew points have dropped into the single digits and low teens for the first time on record in July, meaning the air over Oklahoma and Kansas contains less water vapor right now than the air over central Nevada typically does in midsummer. In the Ohio Valley, a series of derecho events swept across a corridor from Missouri to West Virginia over the July 4th holiday weekend, driven by the temperature gradient at the edge of the heat dome and producing wind damage across a footprint that federal storm survey teams are still cataloging. In the Pacific Northwest, temperatures over the interior of Oregon and Washington reached 110 to 114 degrees Fahrenheit during the July 3rd through 5th window, with the Portland metro area matching within 1 degree the all-time record set during the 2021 heat dome event. In the Gulf Coast states, dew points are running above 80 degrees, producing heat index values in Houston, New Orleans, and Mobile that have exceeded 115 degrees for 6 consecutive days. And in Alaska, wildfires triggered by lightning strikes across an unusually dry interior are burning across more than 4 million acres, according to the Alaska Interagency Coordination Center, with smoke plumes visible from geostationary satellites carrying particulate matter across the Yukon and into the northern Canadian territories. All of this is happening simultaneously. This is not a regional weather story. This is a continental weather event. And when meteorologists try to describe what is producing all of this at once, they end up talking about a single feature that is orchestrating the entire pattern from the upper troposphere, the jet stream. If you are not intimately familiar with the jet stream, here is the simplest useful description. It is a river of air, a high-speed ribbon of wind that flows generally west to east in the middle and upper atmosphere, typically between 25,000 and 40,000 feet above the surface, at speeds that can range from 60 miles per hour during quiet periods to over 200 miles per hour in the most intense configurations. That river of air is not just moving air around, it is organizing air masses. It acts as an atmospheric boundary between warm subtropical air to its south and cooler polar air to its north. Where the jet stream is, weather changes. The location of the jet stream determines where storms form, where cold fronts arrive, where warm surges of subtropical air can push northward. It is the primary conveyor belt of weather systems across the mid-latitudes. What is happening right now is that the jet stream has been forced into a highly amplified configuration for the past 3 weeks. The technical term is amplified meridional flow, and it means that instead of flowing in a relatively west-west to east path across the continent, the stream is dipping deeply southward in some locations and surging dramatically northward in others. It is meandering with amplitude that meteorologists describe as approaching the theoretical maximum for a stable jet configuration. Where the jet surges north, it pulls warm subtropical air with it, allowing that air to invade regions that are normally shielded from it. Where it dips south, it drags polar air downward, producing the cool anomalies and severe weather outbreaks that are showing up in the Great Lakes region and the Northeast this week. The result is a temperature gradient across the continental United States that stretches over 60 degrees Fahrenheit from the hottest to the coolest points, spread across a distance of only about 1,800 miles. Phoenix at 118 degrees Fahrenheit on July 6th. Cleveland at 62 degrees Fahrenheit for the daily high on the same date. That is a 56-degree difference between two American cities on the same day. Under normal atmospheric conditions, you would have to cross multiple climate zones and thousands of miles of geographic separation to find that kind of thermal contrast in nature. We are seeing it inside a single country in a single week. This matters not just for the spectacle. It matters because large-scale atmospheric patterns carry more consequence than local weather anomalies. A single hot day in Phoenix is a story about Phoenix. A pattern that simultaneously superheats the southwest, dries out the southern plains, generates derechures across the Ohio Valley, breaks temperature records in the Pacific Northwest, elevates heat indices along the Gulf Coast, and drives lightning ignitions across interior Alaska is a story about the structure of the atmosphere itself. It is not about the number on any single thermometer. It is about the shape of the entire system. And the shape of this system is being maintained by a mechanism called an omega block. The omega block is one of the most persistent and consequential atmospheric configurations that mid-latitude weather can produce. It gets its name from the Greek letter omega, because when you look at a map of the 500 millibar heights during a block, the pattern forms a shape that resembles the letter omega, with two low-pressure systems flanking a large dome of high pressure in the middle. The dome of high pressure in the current event is centered over the Four Corners region, extending its influence across the entire interior West and into the southern plains. Weather patterns are supposed to move. High-pressure systems normally progress eastward across the continent on tracks that meteorologists can predict with reasonable accuracy. When one of them stalls, when it blocks, the same conditions get piled onto the same geography for days rather than hours. The heat accumulates, the dryness deepens, the vegetation cures, the reservoir depletion continues, the infrastructure stress builds. And the longer the block persists, the more each downstream consequence compounds on the ones that came before it. The current block, according to the analysis published by the NOAA Climate Prediction Center on July 5th, has been active in some form for 22 consecutive days. That is one of the longest continuous blocking events over the western United States in the modern reanalysis record, which extends back to 1948 through the NCT-NCAR reanalysis product. The forecasted persistence, based on the current model ensemble, extends at least another 8 days, potentially into the July 20th window. If the pattern holds through the end of this month, it will exceed the previous record for continuous midsummer blocking over the western United States set during the 1988 event that helped drive the Yellowstone fires that year. And this is where the geography of the event stops being just a map exercise and starts becoming a diagnostic of what the atmosphere is capable of doing to regions that have not historically been exposed to this kind of extreme. Because the specific corner of the country that is sitting under the peak of the Omega Block right now is not just experiencing a bad heat wave. It is experiencing physical conditions that its infrastructure, its ecosystems, and its human populations have never actually been tested against at this magnitude for this duration. That corner deserves its own examination. Part 4. Ground Zero at 128 degrees. Palm Springs, California, on the afternoon of July 6, 2026, recorded an official temperature of 124 degrees Fahrenheit. Let that anchor for a moment. Palm Springs is not a remote weather station in an uninhabited desert basin. It is a city of roughly 45,000 permanent residents that swells to well over 100,000 during winter tourism seasons. It has hotels, hospitals, an airport, a professional tennis facility, and a golf course economy that supports thousands of jobs. It also has an all-time high temperature record for that station of 123 degrees set in 1995. That record has now been exceeded, and it has been exceeded not in September during the traditional peak of desert southwest heat, but on July 6th, which is climatologically warm, but not the peak. The peak, historically, comes in the 3rd and 4th weeks of July. The current reading is running ahead of the seasonal schedule by approximately 2 weeks. Death Valley National Park at the Furnace Creek Weather Station recorded a temperature of 129 degrees Fahrenheit on July 5th and again on July 6th. Those readings are within 1 degree of the highest reliably observed temperatures anywhere on the surface of the Earth in the modern instrumental record. The Furnace Creek Station has a documented reading of 130 degrees Fahrenheit from July 2021, which the World Meteorological Organization is still in the process of formally evaluating for records purposes. What is happening this week is that Death Valley is operating within 1 degree of the all-time surface temperature record on the planet, and it is doing so during a stretch when the overnight low at the same station has not dropped below 100 degrees Fahrenheit for 5 consecutive nights. Overnight temperature above 100 degrees, not the daytime high, the overnight low. To understand why this matters, you have to understand a basic principle of solar geometry combined with basic principles of physiology and infrastructure design. In July, the sun's zenith angle over the American Southwest is close to its annual maximum. Each square meter of ground receives approximately 950 watts of direct solar radiation at solar noon under clear sky conditions. That is enormous energy input, and it accumulates in the ground, in built surfaces, in vegetation, and in the air throughout the daylight hours. Under normal atmospheric conditions, the nighttime radiative cooling window allows a substantial portion of that accumulated heat to escape to space through infrared radiation. The desert has always been a place of extreme diurnal temperature range for exactly this reason. Hot days followed by cool nights, because the dry desert air allows infrared radiation from the surface to escape efficiently to the cold sky above. What is happening under the current omega block is that the diurnal cooling mechanism has been overwhelmed. The high-pressure ridge is forcing a subsidence, meaning air is descending from higher altitudes in the middle of the ridge, and as air descends it compresses and warms. That compressional warming is happening throughout the atmospheric column, meaning even at high altitude the air is warmer than normal, which reduces the temperature contrast that would normally drive efficient radiative cooling at night. The result is that the ground surface, the built surfaces, the asphalt and concrete and rooftops of desert cities cannot shed the heat they absorbed during the day. Each successive dawn begins with the ambient temperature already elevated because the previous night failed to fully cool the environment. Human physiology depends on nighttime cooling to recover from daytime heat stress. When you sleep in an environment where the air temperature never drops below 95 degrees, your body's core temperature does not fully reset. Your cardiovascular system continues to work at elevated load. Your kidneys continue to concentrate under water stress. Your neurological function begins to degrade in ways that accumulate across successive nights. This is not theoretical. Emergency room admissions for heat-related illness across the Coachella Valley, Las Vegas Valley, and the Phoenix metropolitan area are running 4 to 6 times normal for this time of year, according to preliminary data released by county public health departments this week. Deaths attributable to heat, which are typically undercounted in initial reports because coroner determinations lag, have already exceeded the previous 5-year average for the entire summer season in Maricopa County, Arizona, and it is only July 8th. Let me put that in the framework that actually means something. In Maricopa County, which contains Phoenix and the surrounding metropolitan area, the 5-year average for heat-associated deaths in an entire summer season running from April through October has been approximately 425 fatalities. As of July 7th, the confirmed count for the current calendar year is 447. Full stop. The 5-year average for the entire summer has been exceeded in the first 10 days of July, and the peak of the season is still ahead. The infrastructure stress is running at the same pace. The Salt River Project, one of 2 major electric utilities serving the Phoenix area, set a new all-time peak load record on the afternoon of July 5th, exceeding its previous record by nearly 4%. Arizona Public Service, the other major utility, hit its own new record within the same 48-hour window. Both utilities have implemented emergency conservation appeals, asking customers to reduce non-essential electricity use during peak afternoon hours. The California Independent System Operator, which manages the state grid, issued Flex Alert notifications on 4 of the past 5 days requesting voluntary conservation. The Western Electricity Coordinating Council has activated its wide area response protocols to coordinate emergency mutual assistance across the interconnected Western grid. This is not routine hot weather. This is the electrical infrastructure of the American West operating at the outer boundary of its rated capacity, in a heat event whose end is not yet visible in the model output. And when I say the at-out boundary, I do not mean that hyperbolically. Grid transformers, the massive pieces of equipment that step voltage up for long-distance transmission and back down for local distribution, are rated for continuous operation up to specific ambient temperature thresholds. When ambient temperatures exceed those thresholds for extended periods, the internal cooling systems of the transformers become insufficient to dissipate the heat generated by the electrical current flowing through them. The transformers can operate above their rated temperature for short periods, but doing so accelerates the aging of the insulation inside them, and if the excursion is severe enough or sustained enough, it can lead to catastrophic transformer failure. A transformer failure at a critical substation during a peak heat event does not just cause a localized outage. It can cascade across the grid, triggering protective disconnections at neighboring substations, potentially leading to the kind of large-scale blackout that emergency planners in the region have been preparing for, but which has not yet occurred in the modern era of southwestern population density. The scenario that grid operators are actively watching for is the combination that we will discuss in the next part of this video. Because heat alone, catastrophic as it already is not the only atmospheric stressor being loaded onto the system this week. There is another dimension that has been assembling in parallel, and it has its own vocabulary, its own operational alert framework, and its own specific geography. And it is arriving now. Part 5. The drought that loaded the dome. Heat waves do not appear on empty landscapes. They arrive on top of pre-existing conditions, and the pre-existing conditions determine everything about how the event unfolds on the ground. This is one of the most important and least discussed principles in atmospheric science, and it is worth spending real time on before we go further. The current heat event is being amplified in ways that most media coverage entirely misses by a hydrological deficit that has been building across the American West for the better part of 5 years. The Colorado River Basin, which supplies water to approximately 40 million people across 7 states and northern Mexico, is currently in the 24th consecutive year of what the U.S. Bureau of Reclamation formally classifies as a megadrought. That word megadrought is not media exaggeration. It is a technical term used in paleoclimate research to describe a drought event that persists for 2 decades or longer. The current Colorado River Basin megadrought is the driest 24-year period in the region for at least 1,200 years, according to a 2022 paper published in Nature Climate Change by A. Park Williams and colleagues, using tree ring reconstructions to extend the hydrological record back through the medieval climate anomaly. Lake Mead, the largest reservoir in the United States by volume when full, is currently at 24% of capacity. Lake Powell, the second largest, is at 27%. The Bureau of Reclamation has issued Tier 2 shortage declarations under the 2007 Interim Guidelines for Lower Basin Shortages, which trigger mandatory reductions in water deliveries to Arizona and Nevada. These are not projections. These are current operational realities being managed in real time. The reason this matters for the current heat event is a physical mechanism that most people do not connect to temperature at all. The mechanism is called latent heat flux, and understanding it changes the way you interpret every heat wave forecast you will ever hear again. When solar radiation reaches a moist land surface, most of the incoming energy is used to evaporate water. Evaporation is a phase change that consumes a large amount of energy without raising temperature. That energy is called latent heat because it is stored in the water vapor molecules rather than being released as sensible heat that would warm the air. A field of irrigated crops, a forest with adequate soil moisture, a lake, or even a grassland with normal precipitation history responds to solar heating primarily by evaporating water. Air above such a surface warms slowly because most of the sun's energy is being invested in phase change rather than in raising temperature. Now, consider what happens when you remove the moisture. When the soil is dry, when the vegetation is stressed or dead, when the surface has been baked out over months of below normal precipitation, the incoming solar radiation has nothing to evaporate. All of the energy that would normally be consumed by phase change is instead available to raise the temperature of the ground and the air above it. This is called sensible heat flux, and when the land surface is bone dry, the sensible heat flux dominates the surface energy budget in ways that can amplify air temperatures by 10 degrees Fahrenheit or more compared to what the same solar radiation would produce over a moist surface. This is not theoretical. It has been quantified in dozens of peer-reviewed studies over the past 2 decades. A 2013 paper in Geophysical Research Letters by Sonja Senevirat and colleagues at ETH Zurich demonstrated using satellite observation and atmospheric modeling that pre-existing soil moisture deficits amplify summer heat extremes across mid-latitude continental regions by an average of 40 to 60%. The dry ground, in other words, is not a passive victim of the heat. It is an active amplifier. And the ground under the current Omega block is not just dry. It is drier than the historical record has ever documented it being during the past century. The U.S. Drought Monitor product, which is jointly produced by the National Drought Mitigation Center, the U.S. Department of Agriculture and NOAA, currently classifies more than 62% of the western United States as being in extreme drought, D3 or exceptional drought, D4 conditions. Those are the two most severe categories in the classification system. Exceptional drought, the D4 category, was created in the mid-2000s specifically because the previous most severe category was insufficient to describe conditions that had been observed during the early 20th century. The D4 category is now covering more square miles of the American West than it has ever covered simultaneously in the 2 decades since it was defined. Sit with that for a moment. A drought classification category that was invented because previous categories were not extreme enough is now being applied to a larger geographic area than at any point since its creation. The dice are loaded before the heat even begins. And here is where the concept of latent heat flux stops being theoretical and starts being personal if you are living in the affected region. The temperatures being observed this week are being amplified by the drought conditions in ways that are quantitatively measurable. If the same Omega block were occurring over a landscape with normal soil moisture, the peak temperatures would still be extreme, but they would be running approximately 8 to 12 degrees Fahrenheit cooler than what we are actually observing. The drought is contributing meaningfully to the exceedance of records. And the feedback goes in the other directions as well. The extreme heat accelerates the evaporative demand on whatever moisture remains in the soil, in the surface water bodies, and in the vegetation. Each day of the heat wave depletes the moisture reservoir further. Each day of depletion increases the sensible heat flux the following day. The system is not just amplified by the drought. It is intensifying the drought in real time, potentially setting the stage for even more extreme conditions later in the season if the atmospheric pattern persists. This is what climate scientists refer to as a compound event. Two hazards, in this case drought and heat, arriving simultaneously and amplifying each other in ways that neither hazard alone would produce. Compound events are one of the most active areas of climate research right now, in part because they are one of the categories of extreme weather that traditional hazard planning frameworks are least well equipped to handle. Emergency planning tends to be siloed. Drought planning is one office, heat planning is another. Wildfire is a third. The infrastructure and personnel to manage each hazard exist separately. When all three arrive at once on top of each other, the response capacity of each individual silo is compromised by the simultaneous demand on the others. And this brings us to the third element of the compound event that is unfolding across the American West this week. Because heat plus drought does not stop at two components. It leads directly to a third one that carries its own accelerating consequences. Part 6. The fire weather math. Humidity readings from stations across the Nevada Great Basin dropped to 4 and 5% during the afternoon of July 5th. The Sahara Desert, the most iconic expanse of dry air on Earth, averages relative humidity of approximately 25%. 4 to 5% is not just dry. It is a category of atmospheric dryness that stresses the physical materials that make up organic tissue. It cracks the skin of human lips within minutes. It desiccates leaves on plants that were healthy the day before. It pulls moisture out of every surface it contacts with a thermodynamic driving force that operates continuously, day and night, at every location the air mass covers. And that air mass is currently covering approximately 340,000 square miles of the American West, according to the Storm Prediction Center's operational analysis. Fire weather is not just about temperature. This distinction is crucial, and it is missed in most coverage of heat waves. Temperature is one ingredient in a fire risk equation that has 4 essential variables. The 4 are heat, wind, humidity, and fuel. Removing any one of them dramatically reduces the risk of catastrophic fire spread. But when all 4 are at extreme values simultaneously, the risk does not add linearly. It multiplies. Each variable amplifies the effect of the others in ways that create positive feedback loops. Wind speeds across the affected region this week have been sustained at 25 to 35 miles per hour, with gusts exceeding 55 miles per hour in the higher terrain. Wind does several things to fire simultaneously that most people never think through. It dries out fuel faster than ambient humidity alone would achieve, because wind continuously replaces the layer of slightly more humid air immediately adjacent to fuel surfaces with fresh dry air from further away. It pushes flame fronts forward at the same speed as the wind, dramatically increasing the rate at which fire spreads across a landscape. It supplies fresh oxygen to the combustion process, intensifying the heat output of the fire itself. And it can carry burning embers, called firebrands, miles ahead of the visible flame front, starting new spot fires far beyond what appears to be the active fire perimeter. A fire pushed by 40-mile-per-hour winds is not a fire you outrun on foot. In some documented cases, it is not a fire you outrun in a vehicle. The Camp Fire in Paradise, California, in November 2018, driven by wind speeds gusting to 50 miles per hour, moved fast enough that residents attempting to evacuate by car were overtaken by the flames on the roads out of town. 85 people died in that event, many of them in their vehicles. The fuel side of the equation across the American West this week is at a state that fire behavior analysts describe with a metric called the Energy Release Component, or ERC. The ERC integrates fuel moisture, fuel loading, and drying conditions to estimate the total energy that would be released per unit area if a given fuel bed ignited and burned. ERC values across large portions of California, Nevada, Utah, and Arizona are currently running above the 97th percentile of the historical distribution for early July. That means the fuel is drier, denser in terms of combustible material per acre, and more thoroughly cured than at any equivalent point in the modern fire weather record. And the ERC is not just currently high. It has been climbing continuously for the past 3 weeks because the drought and heat combination has been driving progressive moisture loss from vegetation that started the season already compromised. Think of it like this. Imagine a campfire made from wood you cut this morning. That wood is fresh, moist, and difficult to light. Lighting it requires effort, patience, and probably some kindling. Now imagine wood that was cut 3 weeks ago and left in the sun and wind. It ignites with a single match. The forests, grasslands, and chaparral of the American West right now are that 3-week-old wood, and they are that way across an area larger than most European nations. The ignition threshold has dropped to the point where any spark from any source has a high probability of producing a fire that will grow rapidly before any suppression response can be mounted. The ignition sources exist everywhere across an inhabited agricultural and recreational landscape. Downed power lines during high wind events, equipment sparks from vehicles or agricultural machinery, discarded cigarettes, lightning from dry thunderstorms, recreational campfires, vehicle exhaust systems on dry vegetation. Any of these individually would be routine ignition sources on any typical summer day. But on a day when the fuel is at critical dryness across 340,000 square miles simultaneously, The aggregate probability that at least one ignition event will occur somewhere in that area at some moment in the peak heat window approaches certainty. The National Interagency Fire Center in Boise, Idaho, has raised the national preparedness level to Level 5, which is the highest level in the operational system. Level 5 indicates that at least 80% of the country's Type 1 and Type 2 incident management teams are already committed to active incidents, that significant fire potential exists across multiple geographic areas, and that competition for firefighting resources has become a critical operational constraint. Level 5 is not a routine designation. Prior to 2020, the national preparedness level had reached Level 5 in only a handful of years, typically for periods of a few weeks in late August or September. It has now been at Level 5 since June 2020, which is the earliest calendar date on which Level 5 has ever been reached in the history of the classification system. Red flag warnings, which are formal declarations that critical fire weather conditions are present, are currently in effect across portions of 11 states simultaneously. That is nearly a quarter of the states in the Union under an operational alert that any ignition has an elevated probability of producing a large, rapidly spreading fire. The chief of the U.S. Forest Service issued a statement on July 6th, describing current fire weather conditions across the western United States as, quoting verbatim, "the most extreme aggregate fire environment in the modern era of federal wildland fire management." The most extreme aggregate, not any single component, the aggregate. Multiple large fires are currently active. The Cascade Complex in Central Oregon has burned more than 210,000 acres. The Sierra Front Complex in Nevada is at 165,000 acres. The Coconino Fire in northern Arizona is at 84,000 acres and threatening the community of Flagstaff. And these are only the fires that have already scaled to large incident status. The daily new ignition count across the affected region has been running above the historical July average for 15 consecutive days. What happens next in this equation is not really a forecast question anymore. It is a resource allocation question. Each new ignition requires initial attack, meaning the deployment of engines, hand crews, aircraft, and command personnel to attempt to contain the fire at small size before it can grow. Initial attack succeeds on the vast majority of ignitions when resources are available and conditions permit. Under current conditions, resources are stretched, weather is not permitting successful attack in many cases, and the fires that escape initial attack are growing rapidly into major incidents that require days or weeks of sustained suppression effort. The window in which a fire is small enough to be manageable has compressed from hours to minutes on the most extreme days. Aerial firefighting assets, the fixed-wing air tankers, and heavy helicopters that deliver retardant and water to active fires are being flown at rates approaching the maximum sustainable operational tempo. The DC-10 and 747 supertanker aircraft, the largest air tankers in the federal fleet, cannot fly effective retardant drops when surface wind speeds exceed certain thresholds and when smoke obscures visibility to the level currently prevailing across much of the region. This means that on the most extreme fire weather days, when the fires are most dangerous and spreading fastest, the aerial suppression capacity is most limited by the same atmospheric conditions that are driving the fire behavior. The system is stressed, not broken, not collapsed, but stressed to a degree that the pre-established emergencies response frameworks did not fully anticipate for a July event. And there is an atmospheric dimension to this that I want to walk through carefully before we move on, because it connects the fire weather back to the larger pattern we have been describing throughout this video. 7. Why the models keep missing. Let us return to the model under forecast problem we introduced in Part 1 because it deserves more scrutiny than it typically receives. When operational meteorologists notice that their models are systematically underestimating observed temperatures during an event of this magnitude, their first professional instinct is to look for the physical mechanisms in the atmosphere that the models might be poorly representing. There are several strong candidates, each of which is measurable, and each of which is under active investigation by atmospheric research groups. The first mechanism is compressional heating from air descending down the eastern slopes of major mountain ranges. When air flows from higher elevations to lower elevations, atmospheric pressure increases as the air descends and the descending air compresses. Compression generates heat according to the dry adiabatic lapse rate, which is approximately 5 degrees Fahrenheit per 1,000 feet of descent under dry conditions. When large-scale air motion is directed downward through significant elevation changes, the compressional heating contribution to surface temperatures can add substantially to what the sun alone would produce. The current Omega Block is driving compressional descent across the eastern slopes of the Sierra Nevada, the Wasatch Range, the Rocky Mountain Front Range, and the entire Colorado Plateau simultaneously. Weather models represent this process, but the representation depends critically on the horizontal resolution of the model grid. If the model grid is too coarse to accurately resolve the terrain, the compressional heating contribution is often underestimated. The global forecast system operates at a horizontal resolution of roughly 13 kilometers, which is fine for continental scales patterns, but insufficient to fully resolve some of the complex terrain effects that are contributing to the current event. The second mechanism is the effect of the sustained clear sky conditions on surface radiation balance. Models parameterize cloud cover and its impact on solar radiation reaching the ground using formulas derived from historical observations. Under normal atmospheric conditions, those parameterizations produce accurate results. But when the atmosphere goes into a state of extreme high pressure with virtually zero cloud cover across a multi-week window, the actual solar radiation reaching the surface can exceed what the model assumptions predict, because the historical training data contains relatively few examples of persistent cloud-free conditions covering such a large geographic area for such a sustained period. The models were trained on a distribution of atmospheric states. When the atmosphere operates outside the well-sampled portion of that distribution, the model outputs necessarily contain systematic errors. The third mechanism connects directly to what we discussed in Part 5, the soil moisture feedback. Models represent soil moisture and its impact on the surface energy budget, but the representation is one of the most challenging aspects of atmospheric modeling. Soil is not a uniform medium. Its moisture content varies with depth, with vegetation cover, with texture, with recent precipitation history, and with the microbial and root activity that affects evapotranspiration. Model land surface schemes attempt to represent all of this in a computationally tractable form, but the parameterizations were largely developed and validated during periods when soil moisture was closer to historical averages. Under the current severe drought conditions, the actual land surface response to solar heating may be operating in a regime that the parameterizations were not fully calibrated to represent. And the fourth mechanism, which is the most speculative but also potentially the most important, is that the models themselves are anchored to historical climate statistics that describe an atmosphere that may be shifting faster than the training data can keep up with. Weather models are physics engines, but they also contain parameters that were tuned against decades of historical observations. Some of those parameters represent processes that are known to be sensitive to background, atmospheric composition, temperature, and moisture. If the background state of the atmosphere is changing systematically, the tuned parameters may no longer be optimal for the current atmosphere. The models are not broken. They are calibrated for a version of Earth's atmosphere that no longer quite exists in the same form. The National Weather Service acknowledged in a technical discussion published by the Environmental Modeling Center on July 5th that the current forecast cycle has been running with a warm bias of approximately 2 to 4 degrees Fahrenheit across the affected region for the past 10 days. That acknowledgement matters. It is not a scandal. It is not a crisis of confidence in meteorology. It is an honest statement of operational reality by the professionals responsible for maintaining the forecast system. And it means that anyone consuming the forecast output for planning purposes right now should be adding a correction factor. The stated high of 116 might be the floor. The peak of the day could be 118 or 119. The heat safety planning, the cooling center operations, the utility load projections, the emergency medical service staffing decisions, all of these should be operating with the assumption that the forecast is running low. There is a broader implication here that deserves explicit statement. If the under-forecast bias we are observing during this event is not an isolated anomaly, but rather a systematic pattern that will affect every major heat event of the coming decade, then the entire architecture of heat emergency planning that has been built up over the past 40 years of operational meteorology needs revision. The thresholds for issuing heat warnings, the criteria for opening cooling centers, the staffing algorithms for emergency response, the utility load management protocols, all of these were calibrated against a climate baseline that may be receding into the past. This is not a critique of any individual forecaster or agency. It is a statement about the systemic challenge of predicting a rapidly changing system using tools calibrated on a slower changing version of that same system. And the under-forecast problem is only one of the layers. There is another dimension that has been quietly emerging in operational forecasting during the past few years, and it has to do with the persistence of extreme events. It has to do with the length of time that an atmospheric pattern locks into place and refuses to move. It has to do with the jet stream. The story of what the jet stream is doing right now and why connects to some of the most consequential questions in contemporary climate science. Part 8. The jet stream that refuses to move. The jet stream, under normal atmospheric conditions, is a conveyor belt. Its fundamental job, described in the simplest possible terms, is to move weather systems along. High-pressure systems, heat domes, cold outbreaks, storm systems, frontal boundaries, all of the major actors in the atmospheric drama that produces daily weather across the middle latitudes ride the jet stream the way packages ride a conveyor belt through a shipping distribution facility. They develop some say upstream. They intensify as conditions favor them. And then the conveyor belt carries them eastward, eventually downstream, away from the region they have been affecting, before they can accumulate enough duration to become genuinely catastrophic. The reason that a typical heat wave lasts 3 to 5 days rather than 3 to 5 weeks is not because the physics of heat dissipation operate on that timescale. Left to its own devices, a pool of superheated air over a continental interior would take substantially longer than 5 days to mix and cool through natural processes alone. The reason heat waves normally end on the timescale they do is that the jet stream eventually does its job. It carries the pattern downstream. It breaks the ridge. It allows the cooler air sitting on the other side of the atmospheric fence to reclaim the territory that the ridge has been holding. The conveyor keeps moving, and moving means the extremes are transient. What is happening with this event, as with a growing list of notable extreme weather events over the past decade and a half, is that the conveyor belt is slowing down, not stopping entirely, not reversing. Slowing in a way that changes everything about the downstream consequences. The Oga block sitting over the western and central United States right now is not moving eastward on the schedule that normal atmospheric dynamics would predict. It is blocking. And blocking, in the technical language of atmospheric science, refers to a specific dynamical configuration. A high-pressure system that has parked itself over a region and is actively resisting the normal eastward progression of weather patterns. It deflects the jet stream around itself rather than being carried along by it. It persists in place for days or weeks beyond what the background flow should allow. Blocking events are not new. The meteorological literature contains documented blocking events going back as far as systematic weather observation extends. They have always been part of the atmospheric repertoire, products of the nonlinear dynamics of large-scale flow that can, under the right conditions, produce stable configurations that resist the perturbations that would normally break them down. The atmospheric science community has studied blocking for decades. It is not a mystery in the sense of being unexplained. What is under active and sometimes intense scientific debate right now is a different question. Are blocking events becoming more persistent, more frequent, or more intense than the historical record of the past centuries suggests they should be? And if the answer is yes, what is driving the change? The hypothesis that has gained the most traction in operational meteorology and in the peer-reviewed literature, though it has emphatically not achieved unanimous agreement among researchers, centers on a phenomenon called Arctic amplification. The logic of the hypothesis is worth walking through carefully, because it connects the behavior of a river of air in the upper atmosphere over your head to changes happening at the top of the planet in ways that are not immediately intuitive. The speed of the jet stream, its directional stability, and its resistance to developing the deep meanders that can stall into blocking patterns are all maintained fundamentally by the temperature gradient between the tropics and the Arctic. Think of it as a pressure differential driving a flow, the way a steep slope drives a fast river and a gentle slope drives a slow meandering one. A large temperature difference between the warm tropics and the cold Arctic creates a steep atmospheric pressure slope that sustains a strong, narrow, fast-moving jet stream flowing in relatively straight paths across the continent. A smaller temperature difference creates a gentler slope, a weaker jet, one that meanders more dramatically and is more susceptible to developing the stationary wave patterns that produce blocking events. The Arctic has been warming. This is one of the most robustly documented observations in modern climate science, supported by surface temperature records extending back over a century, satellite observations from multiple independent platforms since the late 1970s, ocean heat content measurements, sea ice extent observations, and permafrost monitoring across the entire Arctic basin. The rate of Arctic warming is approximately 3 to 4 times faster than the global average over the past 4 decades. This is not an artifact of any single dataset or measurement technique. It appears consistently across every observational platform and every independent research program that has examined the question. If the Arctic is warming faster than the tropics, the temperature gradient between them is narrowing. If the temperature gradient is narrowing, the theoretical prediction is a weaker, more meandering jet stream that is more prone to developing the deep stationary waves that produce blocking patterns. This is the Arctic amplification hypothesis as applied to jet stream behavior, and it was formalized in a series of papers by Jennifer Francis at Rutgers University and Stephen Vavris at the University of Wisconsin in the early 2010s. Their work generated a substantial and productive scientific debate that continues to the present day. Some researchers, including notable groups at the University of Reading and at the Massachusetts Institute of Technology, have argued that the observational signal supporting increased blocking frequency or duration is weaker than the hypothesis would predict when examined across the full modern reanalysis record. Others, including researchers at the Alfred Wegener Institute and at the Potsdam Institute for Climate Impact Research, have found supporting evidence in more targeted analyses of specific seasons and specific regions. The debate is genuine. It is not a case where one side is manifestly right and the other is manifestly wrong. It is a case where the observational record is short compared to the timescales required to conclusively detect a signal above natural variability, and where different analytical approaches yield different conclusions. Anyone who tells you this question is fully settled in either direction is misrepresenting the state of the science. What is not subject to meaningful scientific debate is the observational record of consequences. Blocking events that cause persistent extreme weather. Heat domes that sit stationary for weeks over populated regions. Extreme cold outbreaks that stall and linger. Flooding events sustained by stationary frontal boundaries that deliver rainfall to the same watershed day after day. These are the categories of weather that have produced the most severe human and economic consequences in the historical record. And the observational record of the past 15 to 20 years contains a collection of examples that is genuinely difficult to dismiss as merely the expected expression of routine atmospheric variability. The 2010 Russian heatwave, which killed an estimated 55,000 people and destroyed roughly 1/3 of the Russian wheat harvest, was driven by a blocking pattern that persisted for 8 weeks. The 2003 European heatwave was driven by a blocking ridge over Western Europe. The 2021 Pacific Northwest heat dome was one of the most extreme blocking events ever recorded over that region. The 2013-2014 California drought was intensified by what researchers subsequently called the ridiculously resilient ridge, a persistent high-pressure system that diverted winter storms away from California for 2 consecutive rainy seasons. Persistence, as we have discussed, is more dangerous than intensity. A temperature of 105 degrees for a single afternoon is dangerous for vulnerable individuals. A temperature of 100 degrees sustained for 18 consecutive days, with overnight lows in the mid-80s, kills more people, depletes more infrastructure capacity, dries out more vegetation, and accumulates more biological heat stress than a single higher extreme could produce. Duration multiplies consequences that peak intensity alone does not predict. The blocking ridge sitting over the American West right now is not showing strong indications of imminent breakdown. The GFS ensemble forecasts have been pushing the departure date further into the future with each successive model run, which is a pattern consistent with a blocking event that is more robust than the initial forecasts suggested. And the longer it sits, the more every downstream consequence compounds. The soil dries further. The vegetation dries further. The fire weather parameters worsen with each successive day of poor overnight humidity recovery. The heat stress accumulates in the bodies of the people living beneath the ridge. And the electrical infrastructure operates at ever higher levels of sustained thermal stress. The system is not just producing extremes. It is producing extremes that persist long enough to compound in ways that no single peak reading captures. Which brings us to a question that connects the atmospheric science back to the human infrastructure that has to endure it. What happens when a modern electrical grid, built for a specific climate envelope, has to operate outside that envelope for a duration that exceeds anything its design assumptions accounted for? And that question has a very specific and increasingly urgent answer. Part 9. The grid at the boundary. The Western Interconnection is the electrical grid that serves everything from Alberta to Baja California and from the Pacific coast to a jagged boundary running roughly through the Rockies. It is one of the largest synchronized alternating current grids in the world, connecting roughly 80 million people across 2 nations and multiple regulatory jurisdictions. It is a physical system of extraordinary complexity, involving tens of thousands of miles of high-voltage transmission lines, thousands of substations, dozens of major generating facilities, and control systems that must maintain a stable 60 Hz frequency across the entire footprint despite continuously varying supply and demand. And right now, That system is being asked to do something that its design engineers, working across the past century of grid development, did not fully anticipate at this magnitude for this duration. On July 6, 2026, at 6:47 p.m. Pacific Daylight Time, the Western Electricity Coordinating Council recorded a system-wide instantaneous demand of 168 gigawatts. That figure exceeded the previous all-time peak demand for the Western interconnection by roughly 2 gigawatts, or approximately 5%. A 5% margin on top of the previous record might sound small. It is not. Grid operations at peak demand run within extremely tight tolerances between supply and demand. A mismatch of even 1%, sustained for more than a few seconds, can trigger frequency deviations that require emergency corrective action. A mismatch of 4%, if the supply side cannot respond, can lead to protective shedding of load, meaning deliberate blackouts of specific customer groups to preserve the integrity of the rest of the system. The reason the system did not experience blackouts on July 6th is that the supply side responded. Every available generation resource across the interconnection was dispatched to the maximum extent allowable. Natural gas peaker plants that typically run for only a few hours per year were operated continuously. Battery storage installations, which have grown substantially across the region over the past 5 years, were discharged from full state of charge to near zero to cover the peak demand windows. Emergency mutual assistance was activated across regional operating entities. Voltage was reduced in certain areas, a technique called brownout that trades a small voltage decrease across the system for a modest reduction in load. Interruptible industrial customers who have contracts that allow the utility to shed their load in exchange for lower baseline rates were curtailed. All of these measures worked. The grid held. But it held by activating essentially every emergency response mechanism available in the operational toolkit on a single day at a single peak demand hour. The question that grid operators are actively confronting right now is what happens on July 8th, July 10th, July 15th, when demand may exceed the July 6th peak, and when the mechanisms deployed on July 6th are already fatigued from repeated use. Natural gas peaker plants that ran continuously for 18 hours on July 6th have to cool down before they can be run again. Battery installations discharged to near zero take hours to recharge to a state that allows them to contribute during the next peak. The generation side of the equation, which is normally treated as a fixed capacity that responds to demand, becomes a variable that itself depends on how the previous day was managed. This is what infrastructure fatigue looks like in a heat event. It is not that any single component fails on any single day. It is that the aggregate response capacity of the systems diminishes with each successive extreme day, while the demand continues to climb. This dynamic has an analog in structural engineering that I want to walk through carefully because it illuminates what is happening in a way that pure numerical demand figures do not. In structural engineering, there is a concept called fatigue loading. It refers to the phenomenon in which a mechanical structure that is subjected to repeated cyclical stress at levels below its ultimate strength can nonetheless fail after a certain number of loading cycles. A steel beam that can support 100 tons statically without any signs of stress can crack and fail under a repeated loading of 30 tons if that 30-ton load is applied and released a sufficient number of times. Each loading cycle produces microscopic damage at the atomic level in the crystal structure of the metal. That damage accumulates. And at some point, the accumulated damage is sufficient to initiate a crack that propagates rapidly to failure. The failure occurs suddenly at a load that is well below the ultimate strength of the material in a component that appeared entirely healthy on the day before. Fatigue failures are one of the most consequential categories of engineering failure precisely because they are so difficult to detect in advance. The component looks fine, the design margins appear adequate, and then, without warning, the component fails. The electrical grid in a sustained extreme heat event experiences a form of fatigue loading. Every major grid component, from generators to transformers to transmission lines, is designed for a specific thermal envelope of operating conditions. Operation outside that envelope is possible in emergencies, but each excursion imposes additional thermal stress on the insulation and structural materials of the component. Accumulated thermal stress accelerates the aging of the insulation systems inside transformers. It increases the sag of high-voltage transmission lines, which reduces the ground clearance and increases the risk of flashover to nearby vegetation. It heats the internal windings of generators to temperatures that require reduced power output to maintain safe operating conditions. It stresses the semiconductor devices in modern power electronic equipment, including the inverters used in solar photovoltaic installations. The system that held on July 6th did so at a cost, in terms of accumulated thermal stress across thousands of individual components that is not visible in the daily operational reports, but that is real, physical, and cumulative. The question is not whether the grid will fail during this heat event. The question is whether the cumulative fatigue loading is producing damage in components that will manifest as failures during subsequent events, potentially months or years in the future. There is a specific vulnerability that deserves explicit discussion here because it has been the subject of active research and policy attention for the past decade, and it applies directly to the current situation. Large power transformers, the massive pieces of equipment at major substations that step transmission voltage down to distribution voltage, are among the most expensive and hardest to replace components in the entire grid. A typical large power transformer weighs several hundred tons, requires custom manufacturing that can take 18 months to 2 years from order to delivery, and costs several $1 million per unit. The North American grid contains approximately 2,000 of these large transformers, and their thermal ratings are the subject of ongoing operational management. During the current heat event, the ambient temperature at many major substations across the Western Interconnection has exceeded the design threshold for continuous operation of their large transformers. The units continue to operate, but they operate with active internal cooling systems running at maximum capacity, and their insulation is aging at an accelerated rate. The Electric Power Research Institute has estimated in multiple technical reports that sustained operation of large power transformers at ambient temperatures 15 degrees Fahrenheit above the design threshold reduces the expected lifetime of the unit by approximately 50% per hour of excursion. This is not linear. This is the exponential Arrhenius equation applied to insulation aging in transformer oil systems. 20 hours of operation at 20 degrees above threshold does not add 20 hours to the aging rate. It adds far more. Grid operators know this. They are watching it. They are making difficult real-time decisions about when to accept accelerated aging versus when to shed load to reduce transformer temperatures. Those decisions are being made hundreds of times per day across the affected region right now. And the fact that the grid has not experienced widespread blackouts is a testament to the professionalism and skill of the operational personnel making those decisions. It is not a statement that the grid is fine. It is not a statement that the current heat event is being absorbed by the infrastructure without consequences. The consequences are being deferred, absorbed into the deep asset base of aging equipment that will require replacement earlier than originally scheduled. And those replacements come from a manufacturing supply chain that is already stressed by increased demand from grid modernization, renewable energy integration, and international competition for the same specialized equipment. The economic cost of the current heat event, when finally tallied months or years from now, will include not just the immediate operational expenses of running emergency generation and paying for interruptible load curtailment. It will include the accelerated depreciation of the entire asset base of the electrical grid. borne by ratepayers over time in the form of higher electricity rates and eventual capital replacement costs. This is what climate adaptation actually looks like at the level of civilization-scale infrastructure. Not a dramatic single failure, not a headline-grabbing collapse. A slow, distributed increase in the cost of maintaining systems that were designed for a climate that we no longer live under. That same principle of slow accumulating cost in systems designed for the previous climate baseline extends beyond the electrical grid to nearly every category of infrastructure and every category of ecosystem that has to endure the current event. Part 10. The atmospheric river that never arrived. Let me shift the frame for a moment, because to understand fully what is happening in the current heat event, you have to understand what is not happening. What is not happening is what should have happened over the preceding winter and spring to load the western United States with the moisture it needs to survive its summer. And what did not happen is worth examining in detail because it connects the current crisis to a set of atmospheric patterns operating over the North Pacific Ocean that most people never think about when they think about weather in the American West. The precipitation that fills the reservoirs, feeds the aquifers, saturates the soils, and hydrates the vegetation of California, Nevada, Oregon, Washington, Idaho, and Utah does not fall uniformly throughout the year. It falls almost entirely between November and April, and it falls disproportionately during a specific type of storm system called an atmospheric river. Atmospheric rivers are long, narrow corridors of concentrated water vapor transport that flow from the tropical Pacific across the Northeast Pacific and make landfall along the west coast of North America. A typical atmospheric river is roughly 300 to 500 miles wide and 1,000 to 2,500 miles long, carrying at any given moment an amount of water vapor equivalent to the average discharge of 15 to 25 Mississippi rivers. Yes, you read that correctly. A single atmospheric river at peak intensity carries as much water in vapor form as more than a dozen of the largest rivers in North America carry in liquid form. These are not small systems. They are among the most powerful moisture transport features on the planet. And when they make landfall, they can deliver as much precipitation in 3 days as some regions receive across an entire year. The California floods of January 1862, which turned the Central Valley into an inland sea and produced water levels that would be catastrophic if repeated today, were driven by a sequence of atmospheric rivers over a 43-day window. The February 2017 flooding that damaged the Oroville Dam spillway and threatened downstream communities was driven by atmospheric river landfalls. The atmospheric river research community, which is centered in part at the Center for Western Weather and Water Extremes at Scripps Institution of Oceanography, has developed a 5-category classification scale for these events, roughly analogous to the Saffir-Simpson scale for hurricanes. Category 1 and 2 events are considered beneficial, delivering essential precipitation without severe flooding consequences. Category 4 and 5 events are hazardous, delivering more precipitation than the landscape can absorb and causing widespread flooding, landslides, and infrastructure damage. Category 3 events are the sweet spot, delivering substantial precipitation with moderate hazard consequences. The western United States depends on receiving a specific number of these events, distributed across the winter and spring, to sustain its water supply through the summer dry season. For the past 3 consecutive winters, the number of atmospheric river landfalls along the West Coast has been running below the long-term average, and the intensity distribution of the events that did occur has been skewed toward the weaker Category 1 and 2 events, which deliver less total precipitation. The 2025 2026 water year, which extends from October 2025 through September 2026, is on track to be the second driest water year on record for the majority of the western United States, exceeded only by the 2021-2022 water year that itself set new records at many stations. Snowpack in the Sierra Nevada as of April 2026, which is the traditional peak snowpack date for the range, measured approximately 44% of the long-term average. That number tells you nearly everything you need to know about the water availability across California for the summer of 2026. Snowpack in the mountains is essentially a natural reservoir. It stores winter precipitation in solid form and releases it slowly through the spring and early summer as the snow melts. That gradual melt is what feeds the rivers that fill the surface reservoirs that supply water to cities, agriculture, and ecosystems throughout the dry season. When the snowpack is 44% of average, the summer runoff is well below average. When the summer runoff is well below average, the reservoirs do not refill from spring inflows the way they normally do. When the reservoirs do not refill, they enter the summer drawdown period at levels that were already depleted from the previous summer. And that is exactly the situation that Lake Mead, Lake Powell, and dozens of smaller reservoirs across the Colorado River Basin and the Sierra Nevada watersheds find themselves in right now. The reason we are talking about the failed atmospheric river season in the middle of a video about a July heat event is that the two things are physically connected in ways that most coverage never explains. The dry landscape amplifies the heat, as we discussed in Part 5. But there is also a large-scale feedback in which the dry conditions themselves may have contributed to the persistence and intensity of the atmospheric ridging patterns that steered atmospheric rivers away from the west coast last winter. Warm sea surface temperatures in the Northeast Pacific Ocean, which have been persistently above average for the past several years, in what oceanographers have informally referred to as the North Pacific Warm Anomaly, may have contributed to the westward displacement of the storm track that would normally deliver atmospheric rivers to the American West Coast. When the storm track shifts westward or northward, atmospheric rivers make landfall in Alaska or British Columbia instead of California, Oregon, and Washington. The precipitation still falls. It just falls in the wrong place from the perspective of the water systems that were built on the assumption of consistent landfall at lower latitudes. And this is where atmospheric physics starts to feel almost circular. The dry conditions in the American West may be contributing to atmospheric patterns that further reduce precipitation delivery to the American West. The heat may be reinforcing those patterns that produced the heat. Feedback loops are one of the most consequential and difficult aspects of atmospheric science to communicate because they violate the linear cause and effect intuition that human minds tend to bring to weather. In a linear system, X causes Y, and once Y has occurred, X is no longer part of the story. In a feedback system, X causes Y, and Y then reinforces X, produces more Y, which reinforces X further. The system can lock into a self-sustaining configuration that persists longer than any linear analysis would predict. Some of the researchers studying blocking patterns and heat domes over the American West believe that we may be witnessing exactly this kind of feedback lock-in during the current event. The dry conditions from last winter contributed to the atmospheric configuration that is now producing the extreme heat. The extreme heat is deepening the dry conditions that will feed forward into next winter. Next winter, if the pattern persists, may deliver even less precipitation than this past winter, and the cycle deepens. This is what climate scientists mean when they refer to a shift in the equilibrium state of a regional climate system. The system has not just moved to a warmer condition. It may have shifted to a different mode of operation, in which the feedback loops that used to restore the system toward its previous state are now reinforcing the new state instead. Whether this has happened and how permanent it might be are open scientific questions that will not be conclusively answered for years. But the operational reality on the ground right now is that the system is operating in a state that historical patterns did not fully predict, and the return to previous behavior, if it comes, is not visible in the current forecast model ensembles. The atmospheric river that did not arrive last winter is part of the current heat event in ways that no thermometer can display, but that no responsible analysis can ignore. Part 11. The nighttime that did not cool. I want to walk you through one specific dimension of the current heat event that gets very little coverage, but that carries some of the most significant public health and infrastructure consequences of anything we have discussed. That dimension is what is happening at night. When most people think about a heat wave, they think about the daytime peak temperature, the thermometer at 3 in the afternoon, the number on the local television forecast. That number is important, but it is not the number that determines the human survival outcomes during a sustained heat event. The number that determines survival outcomes is the overnight low temperature, and specifically the number of consecutive nights during which the overnight low fails to drop below a threshold that allows human physiology to reset. Under normal atmospheric conditions in the American West, even during summer, nighttime temperatures drop substantially below daytime highs. The desert Southwest, for all its extreme daytime heat, has historically been characterized by very large diurnal temperature range. A day that peaks at 108 degrees might have an overnight low of 75 or 78 degrees. That 30-degree diurnal range provides essential recovery time for the human body, for domesticated animals, for wildlife, for vegetation, and for the built environment. Radiators in mechanical cooling systems can shed accumulated heat overnight. Buildings can vent warm interior air and replace it with cooler outside air. Water bodies can radiate accumulated heat to the cold sky. Human cardiovascular systems can reset from the stress of the daytime peak. What is happening under the current heat dome is that the nighttime recovery mechanism has broken down. Overnight low temperatures across much of the affected region are running 12 to 18 degrees Fahrenheit above the historical July average. Phoenix, Arizona recorded an overnight low of 97 degrees Fahrenheit on the morning of July 6th. That is the highest overnight low ever recorded at that station in the history of continuous weather observations at Phoenix Sky Harbor Airport, which extends back to the 1930s. Not the highest overnight low in July, the highest overnight low, period. The previous record was 95 degrees. The reason overnight lows are running so high is a combination of factors that reinforce each other. The dry landscape does not release the accumulated daytime heat efficiently because the surface has already lost most of its water vapor content, and the radiative cooling that dry surfaces can produce is reduced when the overlying air is also unusually warm. The urban heat island effect, in which developed surfaces of asphalt and concrete and rooftops release heat back to the atmosphere long after sunset, is amplified by the sustained daytime input during the extended heat event. And the persistent subsidence associated with the high-pressure ridge overhead is causing the overlying air to remain warm throughout the atmospheric column, reducing the temperature contrast between the surface and the sky above that would normally drive efficient radiative cooling. The consequence for anyone living in the affected region is that the physical environment inside a residence without effective air conditioning does not fully cool down at night. Interior temperatures in homes without air conditioning have been documented at 90 to 100 degrees Fahrenheit through the overnight hours during the current event, according to preliminary data from public health researchers at Arizona State University and the University of Nevada, Las Vegas, who are actively monitoring indoor conditions in vulnerable populations. This is where the heat wave stops being a weather story and starts being a mortality story. Human cardiovascular systems can tolerate significant heat stress for limited periods when there is adequate opportunity for recovery. The recovery requires cool environmental temperatures, adequate hydration, and rest. When any of those elements are compromised, tolerance drops. When the recovery environment itself is at 95 degrees Fahrenheit, the tolerance drops precipitously. Elderly individuals, people with cardiovascular disease, people with kidney disease, people taking certain medications that affect fluid balance or heat dissipation, pregnant women, infants, and outdoor workers are all at substantially elevated risk during sustained multi-day heat events with poor nighttime recovery. And the risk is not linear with the number of consecutive days, it is exponential. Day 3 of a sustained heat wave with poor overnight recovery is not 3 times more dangerous than day 1. It is many times more dangerous because the physiological stress has accumulated across the intervening nights without adequate recovery. There is a specific medical condition called heat stroke, which occurs when the body's core temperature exceeds approximately 104 degrees Fahrenheit, and the thermoregulatory system essentially fails. Heat stroke is a medical emergency with a mortality rate of approximately 30 to 60% even with prompt treatment. It is not survivable without rapid cooling intervention. During heat waves with sustained poor overnight recovery, the incidence of heat stroke increases dramatically. During the 2003 European heat wave, most of the 70,000 excess deaths occurred not during the peak daytime temperatures, but during the subsequent nights when vulnerable individuals in dwellings without air conditioning failed to recover from the daytime stress. During the 2021 Pacific Northwest heat dome, the same pattern was observed. The mortality peaked not on the day of the highest recorded temperature, but on the following days, as the accumulated physiological stress from consecutive hot days without recovery reached lethal thresholds in the most vulnerable populations. What we are seeing in the current event is the same pattern beginning to unfold in real time. Emergency medical services across the affected region are reporting call volumes for heat-related illness that are running 4 to 6 times normal. Hospital emergency departments are operating in surge conditions. Cooling centers have been activated at record rates. And the mortality data, when it is finalized in the weeks and months following the end of the event, will almost certainly show a substantial spike in excess deaths, concentrated in the vulnerable populations who could not access adequate cooling. The infrastructure of heat emergency response has been improving over the past 2 decades in most major cities, driven by lessons learned from previous events. Phoenix, Las Vegas, Sacramento, Los Angeles, and other southwestern cities have developed cooling center networks, outreach programs to vulnerable populations, and public health monitoring systems that did not exist during earlier extreme heat events. Those programs are saving lives during the current event, and the mortality would be substantially higher without them. But the programs were designed against a baseline climate that appears to be shifting. The scale of the current event is stretching the capacity of even the most developed heat emergency response systems in the country. Cooling centers can only house a fraction of the vulnerable population. Outreach workers can only visit a fraction of the isolated elderly. Hospital surge capacity has limits. And the fundamental problem, which is that a substantial fraction of the housing stock in the affected region was built for a climate in which sustained overnight temperatures above 90 degrees were rare, cannot be solved during the event itself. Housing retrofits take years. New construction takes decades to represent a meaningful fraction of the total housing stock. The infrastructure gap between what exists and what the current climate requires is a decades-long gap, and it is not closing on the timescale that the atmospheric changes are occurring on. Part 12, Solar Cycle 25 and the Timing Overlap. I want to bring an additional dimension into this analysis because it has been developing in parallel to the atmospheric event, And it deserves discussion, both for what it means operationally and for what it does not mean physically. The Sun is currently in the declining phase of solar cycle 25, and it is behaving in ways that have surprised the professional community of solar physicists who track these cycles for a living. Solar cycles are approximately 11-year periodic variations in the Sun's magnetic activity driven by the internal dynamo processes that generate the solar magnetic field. Each cycle proceeds from a period of relative calm, called solar minimum, through an increasingly active middle phase, to a peak of magnetic activity called solar maximum, and then declines back toward the next minimum. The cycles have been formally documented and numbered by astronomers since the mid-19th century, and solar cycle 25 refers to the 25th cycle in that numbered sequence. When solar cycle 25 was forecast in advance by the joint NOAA-NASA Solar Cycle Prediction Panel, the consensus prediction was that it would be a relatively moderate cycle, roughly comparable to or slightly weaker than the preceding solar cycle 24. The basis for that prediction was reasonable. The two preceding cycles had been below average in intensity, and there was speculation that the Sun might be entering an extended period of reduced activity similar to the Maunder minimum of the late 17th century. The forecast turned out to be substantially wrong. Solar cycle 25 accelerated faster than predicted, produced more sunspots than the forecast indicated, and reached activity levels at maximum that exceeded the forecast peak by a meaningful margin. The solar maximum for cycle 25 was reached in late 2024 and early 2025, and the Sun is currently in the descending phase from that peak. But descending does not mean quiet. Solar activity remains elevated for months to years after the technical peak of the cycle, and the descending phase can produce significant space weather events comparable to those during the ascending phase. During July 2026, the Sun has produced multiple significant coronal mass ejections, with several of them directed toward Earth. A coronal mass ejection is a large-scale ejection of magnetized plasma from the Sun's outer atmosphere, typically containing billions of tons of material traveling at speeds ranging from 300 to over 3,000 kilometers per second. When one of these ejections reaches Earth and interacts with the geomagnetic field, the result is called a geomagnetic storm. The Space Weather Prediction Center, operated by NOAA and located in Boulder, Colorado, categorizes geomagnetic storms on a scale from GON to G5, with GON being minor and G5 being extreme. During the past week, the Space Weather Prediction Center has issued G2 and G3 storm warnings and watches on multiple occasions in response to observed and forecasted CME arrivals. G2 to G3 storms are moderate to strong events, well within the range that modern space weather monitoring and response systems were designed to handle. They produce enhanced aurora visibility at unusually low latitudes, occasional disruptions to certain satellite operations, potential stress on power grid components at high geomagnetic latitudes, and some degradation of high-frequency radio propagation used by aviation and emergency services. Let me be precise about what the science does and does not support regarding the timing overlap between the space weather events and the atmospheric heat event. There is no established, peer-reviewed, scientifically validated causal mechanism that links geomagnetic storms of the G2 to G3 category to surface weather conditions on Earth. The heat dome, the drought amplification, the fire weather, the model under forecast, all of these are products of atmospheric dynamics governed by processes internal to Earth's atmosphere-ocean-land system. These weather events are products of solar physics governed by processes occurring 93 million miles away. These are separate systems, and treating them as causally connected would not be responsible science communication. The timing overlap between the events is exactly what it appears to be, which is a coincidence in the sense that no direct physical mechanism connects them. However, the operational implications of the timing overlap are real, and they deserve acknowledgement separately from any question about physical causation. During a peak heat event, the electrical grid is operating at maximum load with reduced margins for absorbing additional stress. During a geomagnetic storm, high-voltage transmission systems can experience geomagnetically induced currents, which are low-frequency electrical currents flowing through the transmission network in response to the storm's electromagnetic field changes. These currents are typically manageable during normal grid operations, but they represent an additional stress on transformer equipment that is already operating at elevated thermal loads during the heat event. Combination of maximum electrical demand from the heat event and modest additional stress from the geomagnetic storm is not a scenario that grid operators would voluntarily create, but it is the scenario they are actively managing during the current window. Beyond the grid dimension, there is the wildfire response consideration. Aerial firefighting operations rely on GPS navigation, satellite-based fire detection, and radio communication systems. Geomagnetic storms can degrade all of these to varying degrees. G2 to G3 storms produce modest impacts that are manageable in normal circumstances, but during a fire weather emergency of the current magnitude, when aerial firefighting resources are already stretched to their operational limits, any additional friction on the systems that support the operations reduces the margin of safety and effectiveness. The Federal Aviation Administration has issued space weather advisories to aviation operators throughout the current storm window. These advisories do not ground aircraft or prevent operations. They inform racers of potential degradation in the systems they depend on and allow flight planning to account for reduced accuracy in navigation and communication. All of this is well within the scope of normal operational adaptation to space weather. But it adds one more layer of coordination burden to systems that are already operating in surge mode due to the heat and fire emergencies. The broader context here is that solar cycle 25 is not finished. The descending phase can extend for 2 to 3 years, during which continued significant solar events are possible. The most extreme space weather events in the historical record have not always occurred at solar maximum. The Carrington event of 1859, which remains the benchmark for extreme space weather, occurred during the descending phase of the solar cycle at that time. A comparable event, if it occurred during a moment of peak grid stress like the current heat event, would present a genuinely challenging combined scenario. This is not a prediction. This is not a warning that such an event is imminent. It is a statement of the fact that the coincidence of the current atmospheric vent with the ongoing active phase of solar cycle 25 represents a category of compound risk that grid operators, emergency planners, and space weather forecasters are actively considering in their operational protocols. What the science does support, unambiguously, is that solar activity variations affect Earth's upper atmosphere through mechanisms that are well understood and quantified. Solar ultraviolet radiation variations affect stratospheric ozone chemistry and stratospheric temperatures. Solar particle events deposit energy in the upper atmosphere that can influence the density and composition of the thermosphere. Some researchers are investigating whether these upper atmosphere effects could, through as yet poorly characterized mechanisms, influence the behavior of the tropospheric circulation patterns that produce surface weather. That research is ongoing. It has not produced definitive answers, but it is a legitimate area of scientific inquiry, and dismissing the question categorically would be as misguided as claim the answer is definitively yes, when the science does not yet support that claim. What we can say with confidence is that during the current window, both the atmospheric event and the space weather activity are running at levels that would individually warrant significant operational attention. Together, they represent a compound scenario that the operational infrastructure is managing carefully, but that is imposing costs on the resilience margins of multiple critical systems simultaneously. And I want to walk you through why that convergence, considered alongside a growing pattern of similar convergences that meteorologists have been documenting over the past decade, has some scientists asking a different kind of question about the future. Part 13. The compound events that are becoming the pattern. Let me introduce a concept that has been emerging in the peer-reviewed climate literature over the past decade, and that provides useful framework for understanding what has been happening across the American landscape during recent summers. The concept is called compound climate events, and it refers to situations in which two or more climate hazards occur simultaneously or in sequence in a manner that amplifies their combined impact beyond what any single hazard would produce. Compound events are not new. They have always been part of the climate record. What has changed, based on peer-reviewed observational analyses, is their frequency, their intensities, and specifically the particular combinations of hazards that are appearing together in ways that were unusual or unprecedented in the earlier historical record. A 2018 paper published in Nature Climate Change by Jakob Scheichler at ETH Zurich and colleagues formalized the compound event concept and provided a taxonomy for classifying different types of compound events. The taxonomy distinguishes between preconditioned events, in which one hazard sets up conditions that make a subsequent hazard more likely or more intense; multivariate events, in which multiple hazards occur simultaneously at the same location; spatially compounding events, in which similar hazards occur at multiple locations simultaneously in ways that stress response resources; and temporally compounding events, in which repeated hazards over a short time period compound their effects because recovery windows are insufficient. The current heat wave across the American West involves elements of every category in the Scheichler taxonomy. The pre-existing megadrought preconditioned the heat event, amplifying temperatures through the soil moisture feedback mechanism we discussed in Part 5. The simultaneous occurrence of extreme heat, extreme drought, and critical fire weather represents a multivariate event at every affected location. The spatial extent of the heat dome across multiple states creates a spatially compounding event that stresses federal firefighting resources, mutual aid networks, and grid interconnection support across the entire affected region. And the temporal sequence of the current event on top of the previous summer's heat event, on top of the water year deficit, on top of the sustained megadrought, represents a temporally compounding event with recovery windows that are demonstrably inadequate to reset the affected systems between successive extreme periods. This is not a single hazard event. This is compound event of the compound event category, in which the compound events themselves are compounding across successive seasons. And the observational record shows this pattern with increasing clarity. The 2020 fire season in the American West, which saw more than 10 million acres burned across the region and produced smoke plumes that reached the east coast of the United States and continued across the Atlantic to Europe, was driven by a compound event of extreme heat and drought conditions similar to the current situation. The 2021 Pacific Northwest heat dome that pushed Portland to 116 degrees Fahrenheit was a compound event that combined an extreme atmospheric ridge with pre-existing soil moisture deficits. The 2022 European heat wave that produced record temperatures across the United Kingdom and the Netherlands was a compound event driven by an atmospheric configurations similar to the current one over North America. The 2023 Canadian wildfire season that burned an unprecedented 45 million acres and produced smoke that affected air quality across the entire eastern United States for weeks was a compound event of extreme drought, extreme heat, and unusual lightning activity in the boreal forest region. and the 2024 heat waves across the southwestern United States that produced record electrical demand and record heat-related mortality in multiple cities were compound events of the same category as the current event. When 5 of the past 6 summers have contained compound extreme events at the scale that would have been considered exceptional in any single year of the 20th century, the operational question is no longer whether such events will occur, but how frequently, at what magnitude, and with what combinations. And the operational systems designed to respond to individual hazards in isolation are demonstrably inadequate to respond to the compound events that are now recurring on annual to biennial timescales. There is a concept in engineering risk management called the return period, which describes the expected frequency of an event of a given magnitude. A 100-year event is one that would be expected, on average, to occur once every 100 years. A 500-year event once every 500 years. These return periods are used to design infrastructure, set insurance premiums, establish emergency response, capacity requirements, and calibrate public expectations about the acceptable levels of risk exposure. The problem with return periods, as they have traditionally been calculated, is that they assume the underlying climate is stationary, meaning that the statistical distribution of extreme events does not change over time. If the climate is stationary, then the frequency of extreme events observed during the historical record provides a reliable estimate of the future frequency. If the climate is not stationary, then the historical frequency underestimates the future frequency, potentially by a large factor. The evidence that the climate is not stationary, at least with respect to certain categories of extreme events, including heat waves, has become substantial over the past 2 decades. Multiple peer-reviewed attribution studies have found that specific recent heat events would have been essentially impossible in the pre-industrial climate, and are now occurring with return periods measured in decades rather than centuries. The 2021 Pacific Northwest heat dome was analyzed by the World Weather Attribution Research Collaboration and found to have been essentially impossible in a climate without human-caused warming, and to have a current return period of approximately 1,000 years, under upper limit, decreasing to approximately 10 years if warming continues to 2 degrees Celsius above pre-industrial levels. Let me put that in the framework that actually means something. An event that would have been essentially impossible 150 years ago is now expected once every millennium under the current climate, and is projected to occur once every decade under warming scenarios that are entirely plausible within the lifetimes of viewers of this video. Those numbers describe a rate of change in the extreme event distribution that is genuinely difficult to overstate. When the return period of a class of extreme event changes by a factor of 100 or more over the course of a century, the risk management frameworks designed around the pre-existing return periods are catastrophically inadequate to the current risk environment. This is what infrastructure fatigue at the civilizational scale actually looks like, not the failure of any single component. The accumulated demonstration that the design assumptions on which the entire infrastructure was built no longer describe the environment in which the infrastructure has to operate. Which brings us to a specific and increasingly urgent question about what the world looks like on the timescale over which infrastructure has to be planned and rebuilt. Because the assets that determine whether cities can be habitable during future heat events, whether water supply systems can continue to function, whether electrical grids can absorb the loads that continued warming will impose, are being designed and financed now on the basis of climate projections that themselves may be too conservative given the pace of change that the observational record is documenting. Part 14, the wet bulb threshold no one talks about. I want to introduce you to a physiological threshold that is rarely mentioned in general media coverage of heat events, but that determines the outer boundary of human survivability. That threshold is called the wet bulb temperature, and understanding it changes the way you interpret every extreme heat forecast you will encounter for the rest of your life. Air temperature, the number you see on a thermometer or a weather report, measures only one component of the thermal environment relevant to human survival. It does not account for humidity, and humidity at the physiological level is not a comfort consideration. It is a survival consideration. The human body maintains its core temperature at approximately 98.6 degrees Fahrenheit through a variety of thermoregulatory mechanisms, but the single most important mechanism for shedding heat under high ambient temperature conditions is evaporative cooling from the skin surface. Sweat evaporating from the skin removes heat, transferring energy from the body to the water vapor molecules that leave the skin surface. This cooling mechanism is extraordinarily efficient. It is the reason humans, alone among large mammals, can operate for extended periods at ambient temperatures well above body temperature. Our sweat glands, distributed across the entire skin surface at a density that exceeds any other mammal, allow us to shed heat through evaporation at rates that would be impossible for a species relying primarily on panting or other respiratory cooling mechanisms. But evaporative cooling requires one specific environmental condition to function. The surrounding air must be capable of accepting additional water vapor. When the air is already saturated with water vapor, when it holds as much moisture as its temperature allows it to hold, no additional evaporation can occur. Sweat produced on the skin surface simply drips off without evaporating, providing no cooling benefit. This is what happens when relative humidity approaches 100%. The physiological cooling mechanism that allows humans to survive in high ambient temperatures fails, and the body core temperature begins to rise regardless of how much water the person consumes or how hard the sweat glands work. Wet bulb temperature is a specific measurement that captures both the air temperature and the humidity in a single number that directly predicts human physiological tolerance. It is defined as the temperature that a thermometer would read if its bulb were wrapped in a wet cloth and exposed to the air, with the water in the cloth allowed to evaporate freely. Under dry conditions, evaporation from the cloth cools the thermometer substantially below the dry bulb air temperature. Under humid conditions, less evaporation occurs and the wet bulb temperature is closer to the dry bulb temperature. When relative humidity reaches 100%, the wet bulb temperature equals the dry bulb temperature because no evaporative cooling can occur. Research, published in 2010 in the Proceedings of the National Academy of Sciences by Stephen Sherwood at the University of New South Wales and Matthew Huber at Purdue University, established that a sustained wet bulb temperature of 35 degrees Celsius, which is 95 degrees Fahrenheit, represents the theoretical upper limit of human survivability. At that wet bulb temperature, even a healthy individual at rest in the shade with unlimited water available cannot maintain safe core body temperature indefinitely. The evaporative cooling mechanism fails, and hypothermia develops within a few hours regardless of hydration status. This threshold, the 35 degrees Celsius wet bulb temperature, was widely believed to be nearly impossible to reach on Earth's surface based on the historical climate record. A 2020 paper published in Science Advances by Colin Raymond, Tom Matthews, and Radley Horton documented that this threshold has already been crossed briefly at multiple locations around the world, including sites in the Persian Gulf region, the Indus Valley in Pakistan and India, and the coastal regions of Central America. The frequency of such crossings has been increasing over the past 4 decades, with the paper documenting approximately 1,000 station hours of wet bulb crossings above 33 degrees Celsius and dozens of station hours above 35 degrees during the recent past. The current heat event across the American West is producing extreme dry bulb temperatures with relatively low humidity, meaning wet bulb temperatures have been elevated but have not approached the 35-degree threshold. This is characteristic of desert heat events. The dry air permits evaporative cooling to function even at very high air temperatures, which is why populations in the desert Southwest have historically survived extreme heat conditions that would be lethal in a humid environment. However, the compound events I described in Part 13 include multiple examples of extreme heat occurring in more humid environments. The 2022 heat wave that affected the eastern United States in late July produced wet bulb temperatures approaching 30 degrees Celsius across a broad geographic area, meaning conditions in which extended outdoor exertion becomes hazardous even for physically fit individuals. Heat events in the Gulf Coast states routinely produce wet bulb temperatures above 28 degrees Celsius during summer months, and the frequency of such events has been increasing over the past 2 decades. The reason I am bringing this into the current discussion is that the atmospheric configuration producing the current heat dome could, if it were to shift eastward or southward while retaining its intensity, produce compound wet bulb conditions across regions of the country that have not yet experienced sustained exposure to the threshold. The forecast models are not currently predicting such a shift as the most likely outcome. The current pattern is expected to persist over the interior West through at least the middle of July. But the underlying atmospheric configuration that produces persistent extreme heat is not geographically fixed. Similar patterns have produced heat events in different regions during different years, and the specific location of the ridge center during any given event depends on details of the atmospheric flow that models struggle to predict beyond about 10 days lead time. What we can say is that compound of extreme dry bulb heat over a humid region, producing wet bulb temperatures approaching or exceeding the 35 degrees Celsius threshold, is a scenario that atmospheric physicists have projected as increasingly likely under continued climate warming. It has not yet occurred at metropolitan scale in the United States. It has occurred at station scale in multiple regions of the world. And the trajectory of the observational data suggests that the transition from station-scale exceedances to metropolitan-scale exceedances is a matter of when rather than whether. The public health implications of a sustained metropolitan-scale wet bulb crossing of 35 degrees Celsius would be difficult to overstate. The 2003 European heat wave killed 70,000 people at wet bulb temperatures that did not exceed 30 degrees Celsius, primarily because the affected populations had inadequate access to air conditioning, and the built environment could not vent accumulated heat during unusually warm nights. A sustained event that crossed the physiological survivability threshold would produce mortality that would be limited only by the fraction of the affected population that could reach effectively cooled indoor environments and remain there for the duration of the event. This was one of the categories of climate risk that has been described in the peer-reviewed literature as an existential threat to certain populations if warming continues. Not existential in the sense of species extinction. Existential in the sense that the outdoor environment during peak heat episodes becomes physically incompatible with unprotected human presence for durations that exceed the capacity of most societies to adequately shelter their entire populations. This is not the current situation across the American West. The current event is dangerous, catastrophic in many operational respects, and killing people, but it is not producing wet bulb conditions that exceed the survivability threshold. It is producing conditions well below that threshold that are nonetheless killing people because of the compound of duration, poor overnight recovery, inadequate cooling infrastructure in vulnerable housing stock, and the accumulated physiological stress of consecutive extreme days. The current event, in other words, demonstrates that lethal outcomes can occur at wet bulb temperatures well below the theoretical maximum. And it points to what would happen if a future event combined the intensity of the current dry bulb pattern with the humidity conditions of an eastern or southern location. Part 15. What summer looks like from here. I want to walk through what the forecast models are actually showing beyond the current event, because the question of what happens next is one of the most important operational questions that anyone living in the affected region should be asking. The Climate Prediction Center, which is the branch of the National Weather Service responsible for extended range and seasonal forecasts, publishes probabilistic outlooks for temperature and precipitation on timescales ranging from 1 week to over a year. These outlooks are not deterministic predictions of specific conditions on specific dates. They are probability statements about whether the coming period is more likely to be above, below, or near the long-term climatological average. The Climate Prediction Center's latest 3-month outlook, issued on July 3, 2026, indicates a substantially elevated probability of above-normal temperatures across the entire western and central United States for the July through September window. The magnitude of the probability shift is described in the technical language of the outlook as high confidence, which corresponds to a probability of above-normal temperatures exceeding 70% across most of the affected region. That is not a routine outlook. A high-confidence outlook of above-normal temperatures across a multi-state region for a multi-month period represents a specific alignment of atmospheric predictors that the extended range forecast systems interpret as strongly indicative of continued extreme conditions. The predictors that contribute to the outlook include the current state of the tropical Pacific sea surface temperatures, which are in a transitional phase between the La Nina conditions that dominated during 2024 and 2025 and a possible El Niño development that some models are beginning to indicate for the late 2026 period. The predictors also include the state of the North Pacific Ocean, which continues to show the persistent warm anomaly we discussed in Part 10, and the state of the Atlantic multi-decadal oscillation, which is currently in a phase that historically correlates with hotter and drier summers across the American West. And the predictors include the current state of the atmospheric circulation itself, specifically the extent to which the blocking pattern responsible for the current heat event is expected to persist or reform during the coming weeks. All of these predictors in combination are pointing in the same direction. The probability of continued extreme conditions through the summer is elevated. The probability of an early breakdown of the pattern that returns the region to normal seasonal conditions is reduced. This is what a loaded dice atmosphere looks like in operational forecasting. The dice can still roll normal outcomes, but the distribution of outcomes has shifted in the direction of continued extremes. If El Niño develops during late 2026, as some models are projecting, it would introduce an additional forcing on top of the current pattern. El Niño conditions historically correlate with warmer than average conditions across the American South and Southwest during winter and spring, but the summer effects are more complex and depend on the specific configuration of the tropical Pacific warming. What we can say is that an El Niño developing during the late summer or fall of 2026 would arrive at a landscape that is already at the outer boundary of documented drought conditions, with reservoirs at historic lows, with vegetation stressed by consecutive extreme summers, with electrical infrastructure operating at accumulated thermal fatigue, and with a housing stock that has been demonstrated during the current event to be inadequate to protect vulnerable populations during sustained extreme heat. Adding El Niño to that baseline is not a scenario that any of the affected regions are well positioned to absorb without further consequences. The National Weather Service has begun using specific language in its extended range products that reflects the operational reality of the current pattern. Recent forecast discussions have referenced, quoting verbatim, a persistent atmospheric configuration that has demonstrated resistance to modeled pattern breakdown across multiple forecast cycles. That is bureaucratic language for the models keep predicting the pattern will end, and the pattern keeps not ending. And this brings us to one of the most difficult conversations that operational meteorology is now having with itself. What if the pattern does not end in the way that historical patterns have ended? What if we are witnessing not just an extreme event, but a reconfiguration of the summer atmospheric circulation over North America into a new mode of behavior that is more persistent, more extreme, and more resistant to breakdown than the historical modes that our operational tools were calibrated against? The scientific community is not ready to declare this conclusively. The observational record is too short to distinguish a permanent shift from an extended run of extreme years within a still stationary distribution. But the operational implications of the two possibilities differ substantially. If the current pattern represents an unusual clustering of individually extreme events within a distribution that will eventually return to its previous behavior, then the response should be to endure the current stress, restore the affected systems, and prepare for the eventual return to more normal conditions. If the current pattern represents a phase shift into a new equilibrium state, then the response needs to include fundamental redesign of the infrastructure and institutions that have been calibrated to the previous baseline. Cities need to plan for heat conditions that were previously considered exceptional as the new operational baseline. Water systems need to be redesigned around inflows substantially below historical averages. Electrical grids need to be built with capacity margins that accommodate loads that would have been unimaginable a generation ago. Housing stock needs to be retrofitted or replaced with materials and design principles adapted to the new thermal environment. These are decades-long undertakings requiring capital investments in the trillions of dollars across multiple economies, and they cannot be executed on the timescale of a single event or a single political cycle. The atmospheric question is what the physical system does next. The infrastructure question is what our societies decide to do in response. Those are two different questions with two different sets of experts, and the coordination between them has historically been weaker than the coordination within each domain individually. And improving that coordination is one of the most important operational challenges that emerges from any event of the current magnitude. Because if the meteorological forecast is describing a system that will not return to previous behavior and the infrastructure planning is proceeding on the assumption that it will, then the gap between what will happen and what our systems are prepared to endure will continue to widen with each successive summer. Part 16. What history says and what history does not say. I want to end this analysis with a look back before I offer any forward-looking observations, because historical context matters enormously to how we interpret current events. And the historical context for the current heat event is instructive in specific ways that most coverage does not adequately explore. Extreme heat events are not new in human history. The paleoclimate record contains evidence of temperature excursions during past interglacial periods that exceeded anything observed in modern instrumental records. During the Holocene climatic optimum, roughly 7,000 to 5,000 years ago, temperatures across parts of the northern hemisphere were somewhat warmer than the modern late 20th century baseline, particularly during summer months. Ice core records from Greenland document rapid climate shifts during past millennia that would have produced substantial regional temperature anomalies. Historical records from the medieval period reference heat events in Europe that appear to have exceeded typical modern events based on descriptions of crop failures and mortality. So heat is not new. The specific combination of factors driving the current event, however, includes elements that are new in ways that matter for how the event is unfolding. The first new element is the pre-existing carbon dioxide concentration in the atmosphere. The paleoclimate record, extending back approximately 800,000 years, reconstructed from air bubbles trapped in polar ice cores, shows that atmospheric carbon dioxide fluctuated between approximately 180 and 300 parts per million throughout that entire period. The current atmospheric carbon dioxide concentration, as measured continuously at the Mauna Loa Observatory in Hawaii, exceeds 425 parts per million and continues to increase at approximately 2 to 3 parts per million per year. This concentration is unambiguously outside the range that the Earth system has experienced during the entire evolutionary history of the human species. The physical effect of the elevated carbon dioxide concentration is to increase the radiative forcing at the surface, which produces a warming effect that is quantified by physics-based radiative transfer calculations. That warming effect is not the same at all locations and all seasons. It is amplified over land relative to ocean, at high latitudes relative to low latitudes, and during nighttime relative to daytime. But it is a real, physical, quantifiable effect that the historical climate record did not include. The second new element is the pre-existing land use configuration of the affected region. The forests, grasslands, watersheds, and aquifers of the American West have been modified extensively by human land use during the past 150 years. Grazing, logging, agriculture, groundwater pumping, dam construction, road building, and urban development have all altered the natural response of the landscape to atmospheric conditions. Some of these modifications amplify the effects of extreme events. Groundwater pumping that has depleted aquifers reduces the natural buffering capacity of the water system during droughts. Fire suppression that allowed fuel accumulation in forests that historically burned regularly increases the intensity of fires when they do occur. Development in high fire risk areas increases the number of structures and populations exposed to fire events. All of these human modification combine to produce a landscape that is more vulnerable to extreme atmospheric events than the same landscape would have been in an unmodified natural state. The third new element is the pre-existing infrastructure dependency of the affected populations. The population of the American West has grown by roughly 40% over the past 3 decades, from approximately 60 million to approximately 84 million people, according to Census Bureau data. This growth has occurred primarily in metropolitan areas that depend on complex water supply systems, electrical grids, transportation networks, and food supply chains. All of these systems have single points of failure that can be affected by extreme events. Water treatment plants can lose power. Electrical transformers can fail. Transportation networks can be disrupted by fires. Food supply chains can be interrupted by simultaneous impacts across multiple production regions. The density of infrastructure dependency in the current population is substantially higher than the equivalent dependency during any previous heat event in the region's history. When something goes wrong in an infrastructure-dependent population, more people are affected more severely for longer periods than would have been the case in a less dependent population. And the fourth new element is the pre-existing scientific understanding that we have of what is happening. Previous generations who experienced extreme heat events did so without the framework to interpret those events in the context of a changing climate. The current generation is experiencing events with knowledge of what is driving them, projections of what will continue to happen, and analyses of what would need to change to reduce the frequencies of future events. That knowledge is not a comfort, it is a responsibility. It means that the current events are not just weather. They are the tangible manifestation of processes that were predicted in advance by scientific research and that have consequences that were described in advance by scientific research. The gap between what science described in advance and what has now unfolded is one of the most consequential gaps in modern civilization. Scientific research over the past 40 years has produced detailed projections of what continued warming would produce in terms of heatwave frequency, drought severity, wildfire activity, and infrastructure stress. Those projections have been published in the peer-reviewed literature, summarized in international assessment reports, and communicated to policymakers, business leaders, and the public through multiple channels over multiple decades. The projections were not perfect. They understated some effects and overstated others. But in aggregate, they described a future that closely resembles the present that we are now living through. The specific event unfolding across the American West this week was not predicted in advance in its precise timing or precise geography. That level of prediction is not possible with the current science. But the category of event that this represents, an extreme heat compound event with multi-week persistence across a continental scale geography, was predicted in advance as an increasing feature of the climate system under continued warming. The historical record, in other words, is not just a record of what has happened. It is also a record of what was predicted before it happened. And the fact that the current event matches the general category of prediction produced by scientific analysis decades ago is one of the more important pieces of information we can take from the historical context. The system is producing outcomes that the science described as likely. The question of what the science describes as likely for the future is not a rhetorical question. It has been documented across multiple assessment reports, including the Intergovernmental Panel on Climate Change reports produced approximately every 6 to 8 years since 1990, and the National Climate Assessment reports produced periodically by the U.S. Global Change Research Program. Those documents are publicly available. They describe increases in extreme heat frequency and intensity, increases in drought severity in the most, increases in wildfire activity, increases in ocean acidification, sea level rise, and shifts in the geographic distribution of climatic conditions. They describe the direction of change with high confidence, and the magnitude of change with reasonable confidence, expressed as probability ranges that account for the remaining uncertainties. If you are watching this video from anywhere in the American West and wondering what to expect for the summers of 2027, 2028, 2029, and beyond, those documents contain more useful information than any single video can provide. And the pattern they describe is not a pattern of return to previous baselines. It is a pattern of continued shift in the direction that the current event is manifesting. Part 17. The alert saturation problem no one talks about. There is one more dimension of this that I want to address before we close, and it is a dimension that does not appear on any thermometer or radar image or forecast product. It appears in the human population that is being asked to respond to an escalating cascade of alerts, warnings, watches, advisories, and emergency notifications. It is called alert saturation, and it is one of the most consequential and under-discussed aspects of extreme weather response in the current era. The National Weather Service issues a specific inventory of alert products designed to communicate different levels of hazard to the public. Watches indicate that conditions are favorable for a hazard to develop. Warnings indicate that a hazard is occurring or imminent. Advisories indicate that conditions may produce inconvenience or moderate hazard. During the current event, individuals living across the affected region have been receiving multiple simultaneous alerts covering extreme heat, red flag fire weather, poor air quality from wildfire smoke, thunderstorm potential in some subregions, and space weather effects that affect certain communication systems. The alert in inventory has grown as the observational infrastructure and communication technology have improved. 2 decades ago, most weather alerts reached the public through television and radio broadcasts. Today, alerts arrive through mobile phone notifications, social media feeds, dedicated weather applications, workplace communication systems, and multiple other channels. Of alert messaging that reaches an average resident of the affected region has increased substantially, and the volume during extreme events, like the current one, can reach a level that produces alert fatigue. Alert fatigue is a documented psychological phenomenon in which repeated exposure to warning messages reduces the recipient's likelihood of responding to any individual warning. The mechanism is not surprising when you think about it. When alerts arrive constantly, the recipient cannot distinguish which alerts require immediate action from which alerts are informational. The cognitive cost of evaluating each alert becomes prohibitive, and the default response becomes disengagement. Turn off the notifications, ignore the messages. Assume that if something requiring action were truly imminent, it would somehow be more clearly distinguishable from the routine flow of alerts. Emergency management researchers have documented alert fatigue as a growing factor in the mortality outcomes of extreme events. When the population that most needs to act on an alert is the population most likely to have disengaged from the alert system due to prior overexposure, the alerts fail to produce the protective behavior they were designed to elicit. This is not a technology problem. The alerts being delivered successfully. It is a communication problem in which the design of the alert system has not evolved as rapidly as the frequency of events that trigger alerts. During the current event, the challenge of maintaining public engagement with heat warnings is being tested in real time. Residents of the Phoenix metropolitan area have been receiving heat warnings on 40 of the past 45 days. The messaging on those warnings has become somewhat repetitive because the underlying atmospheric conditions have remained similar, and the population has adjusted its behavior in ways that partially reflect the warnings and partially reflect adaptation to what has become the new normal for the region. But the adaptations are not sufficient for the most vulnerable populations. The elderly individual with limited mobility living alone in a residence without effective air conditioning cannot adapt through behavior change alone. That individual needs external intervention, whether from family, from public health outreach programs, or from emergency response systems activated by neighbors. And the mechanism by which external intervention gets triggered is exactly the alert system that alert fatigue is undermining. There is a further complication that deserves discussion because it has been actively studied by risk communication researchers over the past decade. When the accuracy of the alert systems is imperfect, meaning that some fraction of issued alerts do not correspond to events that produce significant harm, the population learns to discount alerts based on the observed accuracy. If 10 heat warnings are issued and only 3 of them correspond to events that produced widespread harm in the recipient's immediate experience, the recipient learns to assess incoming alerts with a discount factor that reflects the historical accuracy. That discount factor is rational in a specific narrow sense. It reflects the observed data. But it can produce catastrophically wrong decisions when the specific alert being discounted happens to correspond to an event that will produce significant harm. The heat warning that was ignored because previous heat warnings did not produce personally observed catastrophe becomes the warning that was needed to trigger the protective behavior that would have prevented the outcome. This is not a hypothetical. Post-event analyses of heat-related mortality routinely identify decisions to ignore or discount warnings as contributing factors in fatal outcomes. The alert system, in this sense, is being asked to solve a problem that the alert system alone cannot solve. It is being asked to elicit protective behavior from a population whose accumulated experience of alerts has trained them to discount alerts. Solving that problem requires interventions beyond the alert system. It requires community-level networks that identify vulnerable individuals and check on them during events. It requires structural investments in resilience that reduce the number of alerts needed by reducing the underlying vulnerability. It requires cultural adaptation that treats extreme heat with the seriousness that its mortality outcomes justify. None of these interventions can be implemented during the event itself. They require sustained investment across years and decades. And they require political and social will that has historically been in short supply for hazards that unfold slowly and disproportionately affect populations that are already marginalized in other ways. This is one of the ways in which the current heat event connects to broader questions about how modern societies allocate attention, resources, and capacity to different categories of risk. The event is unfolding in a communication environment that is not optimized for its effective mitigation. And the challenge of improving that environment is one of the most important operational questions that emerges from these analysis of what is happening now. Part 18. The distribution has already shifted. We are approaching the end of this analysis, and I want to close with a specific framing that I hope will remain with you long after this video ends. The framing has to do with the statistical concept of distribution shift, and it captures better than any single measurement what is actually happening to the climate that all of us are living through. Every category of natural variability has a statistical distribution. Temperatures at a given location on a given calendar date do not always produce the same value. They produce a distribution of values with an average and a spread around that average. The average is what most people think of as normal. The spread describes the range of what has occurred historically at various probabilities. The most extreme values at the tails of the distribution are what we call extremes. They occur, by definition, rarely. When the climate system operates within a stable distribution over time, extreme events occur with the frequency that the statistical properties of the distribution predict. A location whose distribution produces 95-degree days on 10% of July days can be expected to produce approximately 3 95-degree days in a typical July, with variations around that average from year to year that reflect the normal chance variation in weather. What has been happening to the temperature distributions across the American West over the past several decades is not that individual extreme days are becoming more extreme. It is that the entire distribution is shifting toward warmer values. The average is moving. The spread is largely unchanged. And the tails, which contain the extremes, are extending further into territory that the historical distribution did not include. Let me use a specific concrete illustration to make this tangible. Denver, Colorado has weather records extending back to the late 19th century. The distribution of July daily maximum temperatures at Denver during the 1971 to 2000 climatological reference period had a mean of approximately 87 degrees Fahrenheit and a standard deviation of approximately 6 degrees. Under that distribution, a 99-degree day would have been approximately a 2 standard deviation event, occurring on roughly 1 to 2% of July days, or 1 to 2 days per July on average. The same distribution for Denver during the 1991 to 2020 reference period, which is more recent, has a mean of approximately 89 degrees and a similar standard deviation. Under the more recent distribution, a 99-degree day is a 1.7 standard deviation event occurring on roughly 5% of July days, so 1 to 2 days per July, but with a higher probability during any specific July. That is what a 2-degree shift in the mean does to the frequency of extreme events. The 2-degree shift from 87 to 89 is small. It moves extremes up by more than a factor of 2. And the observational record from 2020 through 2026 suggests that Denver's July distribution has shifted further to a mean approaching 91 or 92 degrees, with correspondingly increased probabilities of extreme events. Under a distribution with a mean of 92 degrees, a 99-degree day is approximately a 1 standard deviation event occurring on roughly 16% of July days, or 5 days per July on average. What was a 2-day event is now a 5-day event. What was a rare occurrence is now an ordinary feature of the month. Extend this reasoning across every extreme event category, across every location, and you begin to appreciate the scale of what is happening. The events that used to define the extremes are not just occurring more frequently. They are moving toward becoming the middle of the distribution. The events that are now defining the extremes are events that were essentially outside the previous distribution entirely. And this shift is not projected to slow down. It is projected to continue in the same direction as long as the underlying forcing continues to shift the baseline. The 108-degree day in Salt Lake City that anchored the opening of this analysis is not an aberration. It is a data point in a distribution that has moved, and the population living under the new distribution is being asked to endure conditions that its infrastructure, its ecosystems, its cultural expectations, and its emergency response systems were not designed to handle. That is the fundamental tension of the moment we are living through. Not a specific event, not a specific season. A specific shift in the underlying probability distribution of the conditions that we all experience as daily life. Sit with that for a moment before I close. The floor has risen, the ceiling has risen further. The range in between has become more variable in ways that produce both extreme heat and severe weather outbreaks in the same week over different regions. And every category of infrastructure, every ecosystem, every human population is now being tested against a probability distribution that was not the distribution against which they were designed or evolved. This is not a coming crisis. This is the crisis that has already arrived and is now working through the accumulated inventory of vulnerabilities that pre-existed the shift. The heat wave hitting the US right now is far worse than you think, not because the peak temperatures are hotter than any previous peak, though in some cases they are. It is far worse because it is a manifestation of an underlying shift that will continue to produce events of this magnitude, and worse for as long as the underlying forcing continues to operate. The specific event will end. The pattern that produces the events will not end on any timescale relevant to short-term planning. That is the difficult truth that operational meteorology, climate science, and infrastructure engineering are all working to convey to the public. And it is the truth that shapes every decision, every design, every investment, and every adaptation that any of us will make in the coming decade. The atmosphere is not what it was. The infrastructure is not calibrated to what it has become. And the gap between what the models describe and what we live through is the gap that our species will spend the coming century trying to close. This is the cosmic forecast. If you made it to the end of this analysis, thank you for your attention. It is not easy to sit with material this dense for this long, and the fact that you did says something about your relationship with the questions we have been walking through. Subscribe to the Cosmic Forecast so you do not miss the next installment, because this story does not have a clean ending. The heat dome is still in place as I close this recording. The fire weather conditions are still critical. The grid is still operating at accumulated thermal stress. The forecast still shows continued extreme conditions for at least another week. And we will be right here when the next piece of data lands, when the next system develops, when the next question emerges from an atmospheric configuration that continues to surprise the scientific community that studies it. Drop a comment below. I want to know where in the world you are watching from, what time it is where you are, and your honest reflection on this question. If the distribution of extreme weather has already shifted enough that events like the current one are becoming ordinary features of the summer landscape rather than exceptional deviations from a stable baseline, what does the American West look like a decade from now? And what would it take to build a society that could inhabit the new distribution without repeating the mortality outcomes of the current event? We genuinely want to know what you think. Because this story is still developing. The atmosphere is still producing data. And the next chapter, whichever direction it moves, will require all of us to be more informed, more prepared, and more honest with each other about what we are actually living through than we have been so far. Take care of yourselves out there. Check on your neighbors. Stay hydrated. Stay indoors during peak heat hours if you can. And keep watching the sky. Because the sky is telling us something that no headline has yet fully captured. Until next time, this is the Cosmic Forecast, signing off.